Okay, I guess we can have a soft start introducing the agenda for today. So first of all, welcome back everyone for the second day of the IROS workshop, application-oriented modeling and control of soft robots. My name is Federico Renda. I am a co-organizer of this workshop together with Thomas Turtel, Adi Sadati, Cosimo della Santina, and Professor Cecilia Laschi. Today we will have another 7 outstanding invited speaker presentation and 5 poster presentation as well. I would encourage all of you to remain until the end for the panel discussion chaired by Professor Cecilia Laschi, during which we will also announce the awarded poster presentation. Let me remind you, we will have 3 awarded presentation, kindly sponsored by Disney Research. Without further ado, it's my pleasure to introduce you the first speaker for today, Professor Nabil Simaan. Professor Simaan completed his PhD from the Technion Institute of Technology and is currently a professor of mechanical engineering, computer science, and otolaryngology at Vanderbilt University. His research interests include parallel robotics, continuum and soft robotics, and design on new robotic systems for dexterous and image-guided surgical robotics. Today, Professor Simaan will present us a talk about sensing and control challenge for soft robots. Thank you. Now, Professor Simaan, the floor is yours.
Thank you, Federico, for inviting me to participate. I've had a chance to listen yesterday to some of the outstanding talks. I'm going to start my my talk with running the video, and I'll be ready to answer questions towards the end. Thank you for joining. Hello, my name is Nabil Simaan. I'm from Vanderbilt University, and I'm glad to be presenting in today's workshop. If we look at the challenges in modeling soft robots, we are dealing with robots that present a challenge due to kinetostatic coupling. The first set of issues relate to the direct coupling between the kinematics and statics. For example, a change in loading leads to a change in the robot kinematics itself, so that external loading and kinematics are not coupled. There's also is an issue of indirect coupling. Changing in loading in one location affects the locations, the kinematics at other locations in a soft robot. So for example, if we have a soft beanie or a soft robot and we subject it to a load F, there's going to be a resulting change in shape, which in turn not only changes just the kinematics, but also changes the interaction force with the environment if there was a contact in this location. Soft robots present challenges related to uncertainty, to material parameter uncertainty, fabrication uncertainty, and effects of material aging. And they also present challenges due to elastic instability, for example, static buckling, as you can see, can be seen here in this example, or dynamics instabilities. Despite their modeling challenges, soft robots remain attractive for applications, several applications, because of their ability to offer safe interaction. I've listed here several examples from the domain of medical robotics. As you can see, examples of active catheters or implantable devices made for single port access surgery, combining soft robots with granular jamming, magnetically actuated catheters with several beads. And there haven't been much work yet on soft interaction of organs, and there's other opportunities related to MRI-compatible robots limited to delicate interactions. Also, these robots have been used for human-robot physical interaction. Examples include wearable devices here, pneumatically actuated wearable gloves, or robots that use braided pneumatically actuated fingers. And I could foresee additional applications as for intelligent bed surfaces. In addition, field robotics and manipulation applications have been explored. This is an example of a swimming robot by Suzumori using pneumatically actuated bellows. His group also produced manipulation surfaces for manipulating, for example, objects using a sequential powering of pneumatic chambers. There have been other works on swimming robots, including works by Cecilia Lasky's group and Daniela Rus's group. I want to talk today mostly about the potential of robots as implants. I'm going to highlight some of the earlier works that we've worked on in this example here. These are elastomeric devices that are actuated by careful placement of a wire inside the body. The wire is not, or the strand is not connected everywhere to the elastomer. It is, for example, connected only to the tip here. By pulling on it, you can get different equilibrium shapes of this body. And if you carefully design the wire location, you can achieve the desirable shape you want in order to insert it into the body. You can also steer it, and as you can see in this example here, these are snapshots at different levels of strand pull. And this idea basically led to several developments, among which the consideration of using these devices for cochlear implant electrode arrays. Cochlear implant electrode arrays help restore hearing to patients who have lost their hair cells by directly stimulating the auditory nerve through an array of electrodes that receive their electrical excitation through a subcutaneous receiver and an external transmitter with a processor. Luckily for me and for my group, we have had a chance to work with Chris Vellis in the late 2000s, which led to initial formation of IROS surgical robotics. This same concept can also be applied for the design of commercial electrode arrays. As you can see here, this is the Contour Advanced Electrode Array by Cochlear Corporation, and it is comprised of an elastomeric pre-coiled body that is straightened by a stylet. When you pull on the stylet, you basically release the elastomer to achieve its free equilibrium shape, and you get this coiling behavior. So these examples motivate some of the questions that I've been looking at, and my philosophy is that if one generates a very accurate theoretical model for a soft robot, no matter how much effort we divert towards accurate modeling, we are still going to need a model that's going to require an effort of calibration. So the key question that I was intrigued by when looking at devices like these, remember these are very simple soft robots that are actuated by pulling on a strand. And the question was, can we use simplified approaches, and can these simplified approaches benefit rapid path planning for these devices? And can we use the simplified modeling approach to generate optimal designs for these devices, for example, optimizing the actuation placement? And can we use the simplified models for contact detection with the environment, and also contact localization without having a dedicated robot skin? Especially when you have devices that should be miniaturized on the scale of 1 to 2 millimeter in diameter. So motivated by these questions, we can look at a subclass of soft robots. These are robots that evolve when you actuate them on what we call a shape homotopy. A shape homotopy basically says that all of these shapes here can belong to a family of shapes that you could interpolate smoothly between them based on the actuation parameters that you input into your system. In this example, the amount of pulling on the wire. If we look, for example, on the electrode array, I can parameterize it with its arc length S, starting from 0 to L. And also I can characterize any point by the local tangent angle theta of S. And we can follow some of the earlier works of Burdick and Chirikshian on model approaches for modeling the kinematics of hyper-redundant robots. In our case, we look at a model approach for capturing the minimal energy solution for planar implants. So one could parameterize at each location the angle as a function of arc length, location, and actuation as a polynomial combination between polynomial basis functions and modal coefficients. For example, S here is the arc length and Q is the wire pull. And if we define the following modal basis, for example, in this case here, I can define a simple monomial basis. This could be any orthogonal basis, for example, is probably preferred for numerical stability, but since these shapes bend in smooth low and require a low degree in the monomial basis, this is sufficient for our case. We can define modal combinations and ask ourselves, since these modal combinations A of Q define the equilibrium shape for a given wire pull, and when we change the amount of wire pull, we get a continuous change in equilibrium shapes that we call a homotopy of shapes. Then one is inspired to define what we call the modal coefficients as another smooth modal interpolation set. So, for example, each one of those modal coefficients here for a given Q is given an additional modal function combination, as can be seen here. Where eta of Q is a modal basis as a function of the wire strand pull. For soft robots, it could be pneumatic pressure actuation, hydraulic pressure actuation, or any kind of actuation. This is just actuation parameter. In our case, it is the wire pull. And when you do this, we basically obtain a very simple kinematics model, which presents the local tangent to the robot in an interpolation map, double interpolation map, as a function of location and as a function of actuation variable. Even though this is a very simple approach or a very simplistic approach, it can lead to instantaneous kinematics derivations in closed form. It can also lead to direct kinematics in closed form that could be solved very quickly and calibrated very effectively. I want to show you how we do this for a couple of scenarios. So for example, if we look at these robots and we ask ourselves, how do we calibrate this simplified kinematic model that we obtained? Our unknown here is this matrix A, which we will call the unknown characteristic shape matrix. For a given shape matrix, I can calculate psi of S and Q in closed form. So to calibrate the soft robot, we can collect an experimental data set, collect the local tangent angle at R locations along the backbone of the robot, for example, and carry out the experiment for Z values of the wire pull parameter Q. So Z images such as this with R points sampled for local tangent or, for example, for curvature. When we do this, we generate what we call an experimental data matrix filled with the local tangent as a function of location and wire pull. And when you compare it to the model here, we can generate the model equations that should explain the experimental data that we see on this side. And if we call these matrices here omega and gamma, then we need to solve this system of matrix equations with for the unknown matrix A. Solving such systems is easy if we cast them to a standard linear equations with vector unknowns using the Kronecker product, where vector of A is a very long vector containing all of the columns of A stacked in one column. And we can solve in closed form for A. Once we have this simplified kinematic model, which we can compute in real time, we can ask ourselves, how can we actually steer these devices into the body? For example, in this case here, the task is to go inside the cochlea with minimal disruption to the anatomy. Therefore, we define the goal of the path planner is to minimize the shape deviation as captured by these integral squared error between the local tangent angle based on the model and the local tangent angle of the anatomy. And when you do this, you can see, as you can see in this example, you can see the same electrode array going in without actively steering, and this electrode array actively steering. The steering is being triggered by a model and by a external measurement of forces, for example, the insertion force. And you can see when you do this, that this electrode array keeps going because the electrode is actively steering without buckling, whereas here the electrode array buckles. And then we can ask ourselves, extend this concept, where here we're only looking at coordinating the insertion depth with the amount of wire pull. We can extend this path plan to path planning that involve insertion, amount of wire pull, and change of approach angle to optimize insertion. And in this example, we can see that this could have a tremendous benefit in terms of safe insertion into the body. These are some preliminary results. This is what an electrode array without active steering looks like in terms of exponential growth of friction. And this is a same electrode array at different control modes here. In a planar model of the scala tympani, which is a chamber inside the cochlea, and in a 3D model of the scala tympani based on human anatomy. And this is, you can see the results here compared to here. These same results have also been verified in human temporal bones to achieve safe insertion. Once we have these simplified models, we can ask ourselves, can we optimize the design of these robots to achieve a given task? For example, if I have this robot with the wire placed inside, how can I optimize the wire placement? So the goal is to start with an initial wire location path, and we start with simulating the statics of the robot. The statics can be generated in a variety of ways. You could use Coursera model, finite difference. For example, here we use the discretization and the chain method for optimizing this slender body and solving for the equilibrium shape for a given amount of force on the wire. Once we have the statics, we can calibrate the kinematics. And given the kinematics of this simulated electrode array, we can solve for the optimal insertion path plan and calculate the shape fitting error that corresponds with the best optimal path plan that we can get for a given wire location. Then we can update the wire placement using gradient of the shape error and keep searching, keep looping until we converge on an optimal wire placement. This has been shown to work well for devices such as these, going into 2D shapes and 3D shapes using just careful placement of the wire strand. Now that we have the simplified models, we can also use these simplified models to, for example, detect contact on soft robots without having to worry about building a soft robot skin. This applies to soft robots that are miniaturized to a level where developing such an array of electronics at that scale may not be practical. Using that simplified model, we can generate the expected axode of motion when the robot is moving without contact. And when contact occurs, obviously the robot shape, because the robot is soft, is going to change and the kinematics is going to change. Therefore, the axode of motion is going to shift. This axode of motion here is obtained from a sensor at the tip. For example, this could be a magnetically tracked marker or an optically tracked marker. This axode here is the model-based axode based on a free kinematics of the robot. And as you can see, once you get a shift that is above a certain threshold, you can basically trigger a flag that says I detected contact. In this example here, you can see the robot detecting contact. This is with the first segment in a Continuum robot. This is with the third segment in a Continuum robot. And this is multiple collisions, for example. And you can also ask yourself, where is the most likely location of contact that would explain the difference between the externally sensed axode of motion and the model-based axode of motion based on a particular location of contact, and find the location of contact without having a robot skin. And the question is, can this work for soft robots? So we started looking at this. Yu Chen is the first author in an upcoming paper in soft robotics, which looked at these pneumatic bellow actuators shown here. As you can see, this robot, when you inflate it, it bends and it evolves on a what I call a shape homotopy. Using the same approach that I described above, we can simulate and show this is the experimental data. And this is the actual contact location from the experiment. This is the theoretical model that we generate, and we change our guess of where the contact is, and we keep iterating until we minimize the error between the actual contact location and the theoretical contact location that we are guessing. And you can see that the error in localizing the contact here is less than 1 millimeter in this case, based on experimental data collected with that bellow actuator previously. And this also works even if you start guessing the location at the base of the robot, not only at the tip. Finally, since we talked about simplified approaches, I also want to mention that we do look at slightly more complicated modeling approaches for soft robots. For example, looking at solving Coursera-Rod equations for continuum robots. These equations often are computationally expensive to solve, and they require multiple iterations of solving the direct kinematics of these robots and integrating the curvature unknowns. And when you combine this with iterative solution methods such as shooting methods, the integration steps of the direct kinematics could be significant in terms of reducing the computational effort needed for solving these problems. Andrew Arkov has a paper in IROS this year looking at combining the collocation method and the Magnus expansion for closed form integration on Lie algebra to provide a solution, a rapid solution for the equilibrium pose of a continuum device or a continuum beam subject to a loading. Finally, I'd like to mention that soft robot modeling can be tackled by a variety of computational frameworks. However, simplified interpolation models can capture the kinematics while encoding experimentally characterized modeling uncertainties. And simplified kinematics model can also support sensing models, and they can be coupled with to work with for contact detection and localization for soft robots. Computing equilibrium under large deformations requires expensive direct kinematics integration and iteration to find numerical solution of the Coursera-Rod equilibrium equations. For Lie algebra, integration can help to reduce the burden when combined with collocation. I urge you to look at Andrew's paper in this IROS. With regards to open problems in modeling, solutions of large deformations still require heavy assumptions of isotropy and remain computationally expensive. I do not see any particular way of solving this problem in a way that would also account for fabrication uncertainties. But I do see ways of adopting some of the simplified modeling approaches for rapid calibration of these slightly more complicated models. We need new approaches for simplified modeling and calibration of soft robots to overcome the computational burden. Modeling uncertain soft robot kinematics and statics and sensing still remains an unsolved problem. And approaches for dynamic stability theoretically exist, but can be difficult to deploy for robots with multiple degrees of freedom dealing with multiple contacts, for example. And path planning remains a problem due to the modeling difficulties and due to the infinite configuration space and instabilities of these robots. Therefore, using simplified modeling approaches could also help. Finally, I'd like to highlight the references that this talk refers to. And I'd like to acknowledge the funding sources. And thank you all for listening to my talk. Hello.
Thank you very much, Professor Simaan. We have time for a few questions. I saw one in the chat. George is asking if it is reasonable to assume that the interpolation scheme has negligible residual error since you are trying to interpolate highly nonlinear function. And in addition, do you think that the low repeatability of soft structure may be captured by formulating the interpolation problem using random function to quantify the uncertainty?
So there are two things. There is the hysteresis and possible actuation losses, and then there is the nonlinearity of the behavior. The nonlinearity of behavior can be captured with the sufficiently large number of model functions. I'm not so concerned about this. What I'm concerned about is the hysteresis behavior. Hysteresis behavior can be a little bit difficult to capture with a single model basis. What you will have to have there is you can tackle the problem using two approaches. One approach is by trying to characterize the hysteresis uncertainty using a learning approach. We've been successful in using a variety of ways. One of them is using supportive vector machine regression to capture hysteresis loops. We have an upcoming IGRR describing this hopefully soon. And there are other ways where you could capture such behaviors using neural networks, for example.
Thank you. Very interesting. There is another question from Andrew. Thank you for your talk. You mentioned calibration challenge at the end of your talk, such as accounting for manufacturing differences. What has been your lab's approach to calibration so far?
So in this area, I think what we've done so far is establishing a framework for calibrating continuum robots, which are a subset of soft robots. They're slightly easier than soft robots since they don't deform in such unexpected shapes. And we've been able to obtain identification Jacobians. I would also urge you to take a look at some of the works by Federico. I think he had a nice framework, which I think is amenable to slight modification, which could also lead you to a closed form expression of the identification Jacobian. Our approach specifically focuses on trying to identify the modal factors. I think Andrew Orikov presented some of the work yesterday looking at shape sensing. What he presented was also essentially the identification Jacobian, which also could be used for calibration of these devices. With regards to material degradation, this is going to remain a challenge. Characterizing soft robot behavior due to material degradation is going to require longitudinal studies and preferably some intrinsic sensing ability inside the device itself, so you can basically update your model gradually as the device degrades. I am not aware of published efforts in that area. In my opinion, that still remains one of the open research problems for people to look at.
Thank you so much, Professor, for your insightful thought. Now it's time for Marc Killpack. Professor Killpack, are you around?
I am. Yeah, I'm here.
Hi. Hi. Thank you for being here. Morning, everyone. Professor Killpack received his PhD from Georgia Institute of Technology and is now associate professor in the Department of Mechanical Engineering at Brigham Young University. His research interests are related to improving modeling and control for soft and compliant robots with space exploration, search and rescues, disaster response, etc. Today's Professor Killpack will talk about sampling-based optimal control for soft robots. So let me share the video.
Hi, my name is Marc Killpack, and I'll be presenting to you today on sampling-based optimal control with learned models for soft robots. And this is collaborative work between the RAD Lab, Robotics and Dynamics Lab, and the Perception Control and Cognition Lab at Brigham Young University. So as a sample application, or something that we're shooting for in the long term, is to get large-scale soft robots working together in order to do more impressive tasks. So this idea is based on a paper that we presented at RoboSoft this year. And to give you just a quick sample of what that might look like, here you have a large-scale soft robot, and then we have Baxter, which is at least being controlled to be very compliant, and they're trying to execute together a trajectory. Now, this isn't moving impressively fast, and the motion itself isn't particularly complex. But this is the long-term goal, would be to get multiple soft robots working together to be able to improve their payload and task capability. However, the dynamics of tasks like this and the control here is going to be more complex if we want to be able to accomplish this. To give you an idea of the kind of platforms we're working with, most of what I'll present on today uses the platform on the right that's being shown. And there's a source pressure with spool valves that can control pressure being pushed into the actuation chambers. In this case, each of these joints has 4 actuation chambers. You can see it moving around as we change the pressures. The control setup, again, just to give you an idea here, we have the robot itself, and then we have an inner loop, which is for high rate pressure control. And then we have an outer loop, which is for model-based control. And we're doing model predictive control there. And at this point, you might be asking, and if you have experience with soft robots, you might be asking, why would we want to do model-based control? It just seems really difficult. And what you're seeing here is an image of one of the first times with a really soft fabric-based joint that we had tried to do PID control. And one option with a soft robot is just slow the control down, slow it way, way down, and then you can move smoothly. But what we want to be able to do is, even with step inputs like this, or really aggressive movements, can we still get smooth motion? And for that, we believe that we need something like model-based control to be as aggressive as we can while still remaining compliant. So we've talked about the motivation now up to this point. And what I'd like to talk about next then is the limitations of model predictive control with using traditional convex solvers and simplified first principle models for soft robots. This is some of our past work. I'm just trying to motivate, again, a little bit of why the solutions that I'll present today are important. So if you are not familiar with model predictive control, the whole idea here is I have some desired goal state for my robot, which is the red line. I have a predicted state based on a dynamic model, which is the green line. And then I use an optimization to solve for these blue inputs. And over a time horizon, I get to pick a certain number of inputs. And the idea is I'm trying to solve this optimization. But I solve this at every time step. So in other words, I'm always looking a certain time horizon into the future, solving this optimization and doing the very first thing here that's shown in this blue line before I then reformulate the problem and do it again. So for soft robots, the way that we first approached this was we developed a normal dynamics model based on Lagrangian dynamics and making some simplifications. We included first order pressure dynamics, which weren't super accurate, but worked pretty well. And we did this, and then you still have to linearize and discretize the model in order to do model predictive control, at least in the way we were doing it. And even then, the convex solvers weren't fast enough. As we got larger degree of freedom soft robots, I think around 24 states, we couldn't solve fast enough with the convex solver. And so then one of the things we tried was, well, we took each state and we kind of broke up the system of differential equations into n discrete time decoupled equations. And you might ask, well, why would you ever do that? It's going to make your model worse. And that's true. It did make our model worse, but you can see the difference here. If we tried to linearize our nonlinear equations for a soft robot here in the Taylor series and focusing on King Louis, that line right there, then we have 33,000 KKT equations for a convex solver. Whereas if we make that simplification, each optimization problem, we can solve a bunch of them in parallel, and we only have 3,000. So it's an order of magnitude better, right? And this is one of the reasons we were looking at this. However, the problem is approximate models that are necessary to make the problem tractable don't represent the system very well sometimes, especially for more dynamic motions and more complex soft robots. And even by using approximate decoupled models, the convex solver struggled to keep up as the number of degrees of freedom increase. And so I'm going to talk about that a little bit more. Really, we tried to solve this in two main ways. And the first that I'll talk about is by using a sampling-based solver instead of using a convex solver. So we kind of asked ourselves, is there a better way to reduce the optimization size? And we came up with the idea of parameterizing the input across the predicted time horizon instead of trying to reduce the complexity of the model itself. So here, what I'll be showing in this example is we're still using linearized models, linearized and discretized, but we're not decoupling them and making them less and less accurate in that way. So the idea is quite simple. It's just, what if I took where I'd had a number of these blue inputs, and now I say, look, I only get to choose 3 degrees of freedom in that whole horizon. And so I only get to change my input 3 times, but I'm going to forward sample as if I was applying this input across the whole time horizon. Okay? And just to make this clear, in case we're not understanding how the dynamic model is used, I take inputs and I forward simulate. And so, for example, if I have this red desired over the time trajectory, I could forward simulate each of these, the green, the yellow, and the blue, and these would correspond with different inputs that I applied to the system. And if I'm doing a convex solver, I let the convex solver kind of twiddle U and change it based on gradients to find the best U that will minimize the cost, the distance. And so in that case, in these examples, it would be the yellow one. But the idea with what we're doing with sampling-based solver is, so we parameterized. I told you we can only have 3 inputs, but what if we just pick random, and it's not exactly random, but we pick 3 random inputs. We see if we forward predict all 3 of them, what that does in the dynamics, and then we just pick the best one. And this might sound like a naive approach, and at first we thought it might be. So let me finish explaining the algorithm. The idea really is we generate a bunch of random input trajectories. These are our control trajectories. We forward simulate each of these trajectories using linearized dynamics on a GPU. And so we can forward simulate them really fast because it's just some matrix math to do that if the system is discretized and linearized. And we evaluate costs for each one. We choose the best parents, and then you do the normal kind of evolutionary algorithm type thing to pick out the best inputs and then generate a new population. Now, in model predictive control, the whole idea here is I keep my population from one time step to the next. So it's always getting better and better. And my performance as I move forward with my trajectory actually improves in practice. So the results for this, when we did this with a linearized system, was that the actual cost for control, and we did this in simulation first because there we can control the time step. It was only 5 to 10% worse than if we had used a convex solver. So right now, that might not sound too impressive. It's like, well, it's worse. It's worse than the solution you would find with a convex solver. And that's true. But keep in mind the second point, that a convex solver can't solve fast enough in real time for many soft robot models with a large number of degrees of freedom. So the point here is this simple sampling-based method is giving us really good solutions, almost as good as if we gave a convex solver as much time as it wanted, but it's solving it fast enough to actually use in real time. So to show this, these results weren't for a soft robot per se, but what we're showing here is we increase the number of degrees of freedom on a robot that we're trying to control, which again, you can think in your mind, that happens as you try and start to represent a continuum platform like a soft robot. At some point, even as you do lumped parameter models, you're still going to have to increase your number of degrees of freedom to increase the accuracy of your model. As we do that, what you can see here is the black line is the trend of how our solve time for a model predictive control problem goes up as the number of links here on the bottom goes up. So OSQP is a state-of-the-art convex solver. And if we don't do anything clever, then you can see that the solve times get up to about a second when we get up to 13 links for this robot. If we do our smart parameterization, the one I was just telling you about, where we kind of break up the input and only allow it to have a few degrees of freedom, but we still use a convex solver, we get this red line, which down at the low number of degrees of freedom really is just as good or better than the other methods that I'll tell you about. But as we get, again, to higher degrees of freedom, it gets worse. The solve time is about 1/10 of a second. So there's no way we can run this at like 50 or 100 hertz or anything like that for real-time control. And then as you keep going down, what you're seeing actually is versions running on a GPU. And the coolest one to me is this green line that you can see scales super well with the number of degrees of freedom. And that's a Titan GPU that we're running this on. So the takeaway here really is just that if we do this sampling-based MPC and we parameterize, we can solve really large degree of freedom problems really quickly still. So that's exciting. So that's one kind of takeaway. And then the second part here is we can use a learned linear model. And for what I'll show you first, we're still just evaluating this on a CPU. So we can use a learned linear model. And what we did is we took an analytical model we had for this robot, and we actually learned a representation of that analytical model and to get us joint velocities at the next time step. And the reason we did joint velocities is because then we're not requiring the learned model to learn integration or the relationship in the differential equations. We can do that ourselves in the way we've written A and B here, as you can see. So, so we're able to linearize this way, and we've already discretized in the way we learned the model up here. And when we do that, here's the kind of performance we can get using parameterization like I've shown you, but still doing it with a convex solver. So this is running pretty fast, but the model here is approximate. Let that run for a second. So one of the things we want to point out here is we're giving the step commands, and this platform is actually fairly large and fairly heavy. And as it swings around, you'll see that it does a pretty good job of damping out those unwanted dynamics. Again, giving a step input and desired change in position, and we're still not getting a lot of unwanted oscillation. And just to kind of give you an idea of how underdamped this system is, I'm going to fast forward ahead a little bit, and what you'll see is me pushing on the platform. So it really is this underdamped system that left to its own devices would be oscillating a lot. Okay, but the example that I just showed you, it's using a convex solver, and that means it's still slow if we want more joints than what I've shown you here. In other words, as we get to less and less of a kind of discrete joints, and we have a full continuum robot, this might not work very well. And I'm really not making use of the fast GPU evaluation that we were doing with the learned model. So I use a learned model, and I evaluate that learned model with a GPU, but I'm still just using a convex solver to get my solution. And because of this, I can't represent nonlinear effects over the full time horizon. Oops, sorry. So where are we going next with this? Well, what if we combine these two ideas? And this is what I wanted to really share with you today is what if we do sampling-based MPC with nonlinear learned models? So the idea here is we take a DNN with an architecture that might look something like this, where again, we're still just trying to learn a model for the joint velocities. And because we can evaluate this on a GPU really fast, and we can evaluate lots of trajectories, why don't we just use that with our sample-based MPC to get to solve the MPC problem? And this is work that was from ICRA and in our Robotics and Automation letters this year. So really this model for the algorithm itself doesn't change a whole lot, except that right here where we're generating random input trajectories and forward simulating them, we're doing this with a learned nonlinear model. And to give you an idea of what this looks like, let's see, sorry. We're going to play this video. So this is for a 3-link inverted pendulum, and we're just trying to get it to the upright state. So it goes really fast. We'll watch it again. And what this is nonlinear evolutionary model predictive controls on our left. MPPI, which is a state-of-the-art MPC for large degree of freedom systems, is in the middle, and DDP is also on the right-hand side, is also state-of-the-art. And we'll watch this one more time, and what you'll see is the other two that we're kind of comparing against have to do this kind of swing left to right motion at the end to get upright, whereas the nonlinear evolutionary model predictive control finds a solution which is really non-local. It actually spins the joints within themselves to get up to the upright position, which we think this is pretty cool. So to give quantitatively how this looks, you can see that the cost comparing the three across the full horizon is much, much better for an MPC. That's the method I've been sharing with you. And you can also see that in terms of solve time, it's as good as MPPI and much, much better than DDP. And to be fair, MPPI and DDP, these are not optimized implementations of these, but neither is NEMPCA optimized. In other words, all three of these are kind of naive implementations, and what we're seeing is there's a lot of promise in solving the problem this way. And then, you know, can this nonlinear model predictive controller sample-based, can it work on a real platform? And here we're showing yes. Now, there's a caveat here, which I've kind of hidden away in some ways, and not intentionally, but this is the right time to share it. That is that so far, all of the learned models I'm showing you are learned based on the analytical model we wrote down for this platform. And the reason we did that is because we had plentiful data. We could easily generate, you know, tons and tons of data to learn that analytical model and how to represent it. And again, the motivation for this was because then we can evaluate that model on the GPU really, really quick and use a sampling-based MPC to solve the problem. So it's this coupling again of a learned model and a sampling-based method for MPC. So this is a limitation right now, is that we're not using real data in addition to the analytical model. And I'll share why in just a second. So the robot I just showed, maybe you don't think it's soft. It's definitely underdamped, it's definitely compliant, but maybe you don't think it's soft. And so one of the directions that we're pushing right now is looking at really much softer robots. And so to start with this, in collaboration with Dr. Wingate's group here at BYU, we use the Viper simulation, and there's some details here about it. But what you're going to see is this crazy tentacle with 468 states, 267 inputs, and we're using NEMCA here. And so we use a learned model of the tentacle, and what it's trying to do is reach out and touch and follow that block. And what you'll see is when we get down here at the bottom, there's some really interesting interactions where obviously our model isn't good enough. We didn't learn those interactions both within the tentacle and with contact on the ground. And so it's reaching, and then it has this kind of weird whiplash effect. So what does that mean? Well, it means we definitely need to take more data near the edges of essentially our operating space. But what we're excited about here is this is a really complex system that was essentially, once we came up with a way to represent the learned model, was plug and play into NEMCA, almost exactly the same way we were doing it with the platform in the video before. So the potential pros for this is that you can use GPUs for really fast evaluation and solution for the model predictive control problem. You can easily represent nonlinear models. The hope would be you can just collect the data and hit go, but that's future work for now. And part of the reason for that is scalability for real-time evaluation versus model accuracy is something we're working on, but picking the right DNN architecture matters a lot, and we're working through this for real data. Collecting useful real data in order to get a good learned model actually matters a lot. There's this lack of intuition. Explainable AI maybe could help there. There's work that we are aware of and are trying to incorporate. And then there's no guarantees about stability or even generality of the model, which is not great in general for controls work. But we also think that soft robotics, if we want to be successful at controlling soft robots, might take different approaches to control. And so we're willing to try that and then circle back to thinking about how will we prove stability for some of these things. So this we're working on right now is being able to collect data to improve performance even more. So my acknowledgements, I just want to point out this is in large part work funded by the NSF EFRI program, which is in collaboration with PI Joshua Schultz and Michael Keller, the University of Tulsa, Oklahoma. And then these are the students, right? The students, and then here's Dr. Wingate and the graduate students that are working on this project, and to which we're really grateful for all the awesome results. There are other ways besides learned models. I'll just point out that we definitely have tried some adaptive control methods, which have a lot of promise as well, and are a slightly different approach, but we think could also help with handling model error and improving dynamic performance for control. And I will end my talk here and just say thank you for your time.
Excellent. Amazing talk. Thank you, Professor Marc. Can you hear me?
Thank you very much. Yeah, do you want me to take questions now then?
Yes, I can see a few questions in the chat. Yes, from George. Thanks, Marc. Interesting approach. Can you repeat yourself? Do you mind?
Yeah, I got it. I just want to start by saying thanks again to the organizers. I've learned a lot yesterday that was really, I don't know, it's been really good for me to hear from other people in the field, and then also I'm excited for the rest of the day today. So thank you, first of all. So the first question, provided the long time horizons lead to computationally expensive controllers and short horizons might have non-global solutions, non-globally optimal solutions? Do you have a strategy to set the finite horizon of MPC? This is a great question. And the answer right now is, yeah, we set it as long as we can to still run at a reasonable rate. It's not a great answer. But the point kind of is we play with accuracy of the model by changing the neural net to run faster or slower, by the number of internal nodes and hidden layers and things like that. So we play with that to try and get it to run at a rate that we think is reasonable, looking as far as we can into the future. But I think one of the things that's interesting here, and they've seen this in lots of other systems besides soft robots, and I think we're beginning to see it in some of our research too, is that sometimes what you want is something that's globally consistent, meaning I just want the soft robot to end up at the right place. And if I use a really localized model over a short horizon, I might not actually get very good performance. But the opposite is also true. If I only look at the global performance at where I want to end up, I might do really bad things kind of locally because of some of the nonlinearities and valves and valve control and things like that. So yeah, this is a really good question. I don't know that we have a great answer right now. The second question is
a very long one from Andrew.
Sorry?
A very long question from Andrew, but very interesting as well.
Yeah, so I think the question is, I assumed a dynamically feasible trajectory. So let me say what I think, and then please follow up if I've answered incorrectly. We actually don't assume anything dynamically feasible. We just assume that our inputs are within our constrained inputs. So we don't generate pressures that we can't apply. For example, in our soft robots, we say, look, you can randomly generate inputs between these ranges, and then we just apply them to the simulated system. That's it. The fact that it's dynamically feasible is just because we passed it through the dynamics to see what the output would be. We don't actually have to generate any dynamically feasible trajectories before that point.
I can maybe, if we have a moment, I could clarify that a little bit. First, again, thanks. I was thinking more about the objective function where you have, a quadratic penalty on state versus your reference, and then also an input versus your reference. And so presumably that input reference would be something you would generate before actually solving the online optimization problem. And it would be separate than actually, solving the convex optimization. So that's what I was interested in. Yeah.
I see. Yeah, that's a really great question. Okay, so right now we have no cost on UREF. we have cost on you. We will put a cost on you because it has an effect, right? Just don't do crazy things. Sometimes we'll put a cost on change in you, especially for pressures. If your system thinks it can change you really, really fast and that your actual pressure will change, that's sometimes, that's not correct, right? Your pressure dynamics have significant time. So either you model your pressure dynamics really well as well, or you maybe limit how quickly you can change pressure. But right now we're not using UREF, which is something you could potentially do.
Great, thank you.
Excellent. Are there any more questions from the audience? We have still some time. So today we have to fit 2 more posters than scheduled because of some issue from yesterday. So it would be good to save some time, but are there any more questions from the audience for Marc?
Yeah, so if I can briefly ask a question. So I did not fully understood in which class are you taking the inputs? Are just like discretized sequence of steps, or are you looking in some other way of parameterize the input? Because your method is very general. It should be able to handle I don't know, basis function and stuff like that.
Yeah, that's a great question. So one of the things we looked at was polynomials. So right now it literally is just these knot points and they're linearly connected. That's it. It's very, very naive. And for the GPU sampling-based method, the parameterization doesn't matter near as much. For the convex solver, it actually mattered. They had to be linearly connected, or else the problem wasn't a quadratic problem that we could solve with the convex solver. But in the case of the GPU-based version, we looked at polynomials and we were really surprised. We went to higher and higher order polynomials. We looked at a couple different basis sets and we got worse and worse performance. We don't think that's generally true. Like, we know there's probably good good basis sets right out there that are low degree of freedom and represent kind of the richness of what kind of signal you might want. We don't know what they are. And that's one of the research areas that I think we want to go into. That's a really good question.
Thank you.
And there is a new question from the audience. Aida is asking if this method can be used to control the configuration of the manipulator instead of the endpoint and effector position.
Yeah, actually what you saw there was configuration. We were just doing configuration control directly. Yep.
Excellent.
Except for the tentacle, I guess. Sorry, the tentacle was tip. All the other stuff you saw was configuration.
The last video, you mean the Viper simulation video. Okay. Excellent. Thank you, Marc. I have just a small comment that for me, it's truly a presentation for this workshop is application-oriented control of soft robot. I feel that you really hit the target perfectly with this talk. Thank you very much. Okay. So now it's time for our first poster presentation of today. Phuc Bui, if he's around. He will present a poster, Observer Design for a Fabric Reinforced Inflatable Soft Robot. Yes, I can see.
Okay.
Hi. Yes.
Hi, everyone.
You can share your screen if you have any slide.
Can I share my screen now? Okay. My screen now. Hello.
Yes. Please go ahead.
Can you see my screen now?
Yes.
Okay. Great. Okay. So hi everyone. My name is Phuc Bui. It's my great pleasure today to be here in this workshop. Now I will talk about my current research title, Observer Design for Fabric Reinforced Inflatable Soft Robot. Okay, and this is my the content of my presentation. Okay, and this is the soft robots in our projects at the University of Tulsa, Oklahoma State. This is called the Fabric Reinforced Inflatable Soft Robot.
I guess the connection is not very good on that side. Is there any other author of the work of the abstract that want to present the work? Otherwise, I am afraid we need to move forward with the next presentation. Perhaps we can recover this presentation later on. Okay, let's move on then. Is John Garrett Williamson here?
Yes, I'm here.
Hi, welcome, John. Thank you. So Dr. John from the University of Tulsa will present abstract soft robot workspace expansion via smart material. Please.
Yes. Thank you. Let's see, and I will be actually presenting today with Caroline Schell, and she'll be starting off our work. So can you see my my screen? Cool.
Okay. Hi, I'm Caroline Schell, and Garrett Williamson and I will be talking to you today about soft robot workspace expansion via smart material. We're with the University of Tulsa, and our team consists of myself, Garrett, Dr. Michael Keller, and Dr. Joshua Schultz. So our work focuses on fabric reinforced single chambered robots. And sorry, did it change? Okay, there we go. We aim to change the robot's motion by changing the stiffness, altering the stiffness along the chamber wall using magnetorheological fluid to provide multiple degrees of freedom for a typically 1 degree of freedom fabric reinforced robot. So today we'll talk to you about magnetorheological channels and the finite element analysis of a magnetorheological structure. And then Garrett will take you through manufacturing of composite soft robots and experimentally predicted workspace of a magnetorheological robot arm. So we want to realize our goal of a dynamic stiffness in a chamber wall by use of magnetorheological fluid, which is a suspension of ferrous particles in a carrier fluid that's typically oil, and in a field off state, as in no magnetic field application or there's no magnetic field applied to the MR fluid. It appears as the picture on the left, where the particles are disorderly and they're free flowing. Once a magnetic field is applied, in the picture on the right, in the field on state, the particles orient themselves into chains along the field lines. So the mechanical behavior of magnetorheological fluid is directionally dependent on the magnetic field application. Where that comes into play for us is in a truss, as shown in the diagram in the middle of the slide, with a compressive force and a magnetic field coming up their parallel, that will exhibit the maximum amount of stiffening because of those particles increasing the viscosity and forming chains resisting that force. So we plan to explore this using vascular networks in silicon rubber. And an example of this is shown at the top picture. That's a 3D printed PLA truss structure. And then we embedded it in the middle picture in a dog bone mold of dragon skin. And then in the bottom picture, you can see those protrusions sticking out of the mold. That is will serve as an injection port for magnetorheological fluid once we depolymerize the 3D truss inside of the mold. So our finite element analysis model of these networks uses the equations shown above the truss picture on the slide, and that is effective moduli dependent on magnetic field strength. And so for a potential magnetorheological truss network as shown with the configuration on the slide, and a compressive force on that bottom node 4 roller joint, a family of low displacement curves was created, as seen on the right chart. And with increasing magnetic field strength, you can see the slope drastically increases, and we actually get a twofold increase in the stiffness, which is the slope of these lines, from just 0.01 Tesla field strength to 0.02 Tesla field strength. And we believe that it's likely that the elastomer structure stiffening could be greater with optimized truss channel geometry. So now Garrett's going to talk to you more about the manufacturing of our composite soft robots.
Yeah, so while the work of understanding and modeling the truss structure of the magnetorheological fluids that will eventually embed the walls of our robot, we wanted to see what kind of changes in movement we can expect with these stiffening patches changing throughout the robot. So as you can see here, this is our base arm that has no stiffness patch changes, and we chose to curved geometry for it. It's a single chamber fabric reinforced robot, and you can see the sensor locations for our 3D tracking system as well. So first thing to do was to create this arm. We 3D printed molds, as is common in the soft robotics community, and as you can see here, these are the strip molds, the main arm mold, more strip molds, and we clamped and pinned them to prevent movement. We had issues with the core rotating and causing changes in thickness throughout the robot while the silicone was setting. So what you can see here, we chose an arm morphology convention that I'll briefly cover in order to make the understanding of where we put different things better understandable. So we chose a kind of biological convention to go along with the soft robot. So we have dorsal, ventral, anterior, posterior, and then a 0 to 90 degree convention. So what you can see on the right here is a robot arm, soft robot arm that's being prepared to be poured, and on the left side of that arm, running from 0 to 90, is the fabric reinforcement, and on the right side is a modifying stiffness patch that is running from 45 to 90 degrees. So here, what you can see is the unmodified arm's base motion path. So it's pretty predictable. It curves along the fabric reinforcement. Actually, the reason we chose a curved arm was for this purpose. It has a hyperbolic paraboloid base movement rather than just a straight path line movement that you would get with a straight armed robot. So here are two arms that I'll show the videos of. They have the left one has a Dragon Skin 30 strip running along the ventral side, and the right one has a Dragon Skin 30 strip running along the dorsal side. And these cause changes in the arm's motion that you'll see here. So you can see these changes are pretty drastic. The anterior strip side moves along the curves to almost touch its base, while the dorsal sweeps out a very, very wide arcing curve. And yes, these were made with Dragon Skin 10 and have Dragon Skin 30 strips embedded in them. So after we had run many tests with different patches in different locations, we collected together the point data from the tests and generated a convex hull of the workspace that would be as though the robot could change its stiffness to any of the configurations that we tested. What we found was a 6-fold increase in workspace volume from the base arm to the full workspace. And what you can see here, each line represents a single 3D marker, the end effector, and where it was for different tests. And the red one shows the base arm with a uniform rubber composition, no stiffness patches. So as Caroline said, we currently, our model predicts a 2-fold increase in modulus of elasticity, while Dragon Skin 10 to Dragon Skin 30, which are the two rubbers that we use, have a 3-fold increase in modulus of elasticity. But we are confident that with truss optimization and in further work in the area, we can achieve a 3-fold increase. All right, so we want to thank Drs. Michael Keller and Joshua Schultz for their help on this project and for starting the project, along with collaboration from Brigham Young University. And we also want to thank the National Science Foundation for their funding this project through EFRI grant. And we'll take any questions now.
Thank you very much, John and Caroline. There is a question from Godaba. Can you read the chat, John?
I believe so. Let me click away for a second. And
I think that one might. So the question is, interesting concept for variable stiffness and application. Is there a reason for the truss structure? The linkages in the truss structures experience both tension and compression. How is the performance of MR fluids and tension? So the truss structure, trusses are inherently stable. So we just started out with like a really simple Warren truss. And yes, the linkages are in compression and tension. So in compression tests from a previous study, they found that if the field is applied like transverse to the applied force, there's no stiffening effect. And then same if it's actually, if it is a bending up or down, if it's transverse application of the force, there's little to no stiffening effect. So the performance of MR fluids in tension, we are going to conduct tensile tests. So I can tell you later when I have data on that.
Great, thank you. It's also the response of Kodaba, and we all agree with that. Thank you both for the nice presentation. Now we can move on with next poster, next abstract with Andrew Sebelaus. We will try to recover Fook Bui talk next to this one. So Andrew, are you around?
Yep, that's me.
Hi.
So we are, if my understanding is right, we're a little bit behind schedule, so I should try and keep it concise.
Yes, thanks.
Great. I'll share my screen and start this up. All right. So hi, everyone. My name is Andrew Sebelaus. I'm currently a postdoctoral research fellow in the Soft Machines Lab in mechanical engineering at Carnegie Mellon University. And today I'm going to talk about some very preliminary work on using Gaussian process regression for soft robot locomotion dynamics modeling. And maybe unlike some of the other work presented here, we are using this workshop really as more of a way to discuss this, this initial idea and very much want your all's feedback. The example robot that we're going to be using here is one that I hope my colleagues presented yesterday along with the simulation on the discrete elastic rod simulation. This is a star-shaped robot that is actuated by shape memory alloy actuated limbs that moves by extending these limbs. And on either side here, I have some simulations in our simulation environment that show the robot either taking steps on flat ground or performing a passive walking motion downhill. So at a high level, the problem that we're thinking about here is generating gates for robots like this. And what we have in mind is something along the lines of what we've been talking about earlier in this workshop about either like calibration or somehow incorporating knowledge of the robot after we build it in addition to the analytical model. Because we have a very good analytical model, this high dimensional discretized simulation that we've calibrated for one specific robot, but is also a little to try and do something like, for example, trajectory generation in. Not only do we not really need to use all of this, hundreds of elements here, but it's also maybe a little bit unnecessary. So what we're hoping to do is to think about, getting a reduced model in some form that's somehow approximate, but close enough so that we can find a trajectory and then replay it in the simulation and get out either a motion primitive or something like that. And so on the right-hand side here, these are hand-tuned gates for now, but we're hoping to find better ones, basically. And this little workshop talks about the use of Gaussian process regression for this middle step. GPs are an alternative to neural networks. And the reason why we ended up using them is because they are online learning kernel machines. So as a high level, to frame the experiments that we ended up doing, again, exploratory experiments, what this problem looks like is we're trying to learn a transition function from one state to the next. The actual state representation is sort of a separate problem, but assume you have it for now, a reduced dimensional state representation. And we're trying to learn this probabilistically. And given a bunch of data from a high quality simulation, the first step is to choose a kernel function. So folks in learning may be familiar with this. A kernel is some intuition that we have about the covariance between data points that's kind of norm-like here. And so we choose this, and assuming we've somehow identified this for our simulation, we get a one-step prediction from the GP that is normally distributed. And I'm just going to throw up the equation for the mean here, specifically because it looks like conditioning a Gaussian random variable. So there's a lot of intuition that we can end up getting here based on this model. It's very explainable. And then also these K matrices here are where the online part of GPs come in. They are applying the kernel to either a test point or our data set. And so you can imagine here, the concept we had eventually is we go and run this on the hardware robot and start swapping in or out our data online. And this means that we don't have to, for example, retrain a neural network every time we get a new data set. So hopefully this, this would help with the, all-encompassing calibration issue. So now the question is how to apply a method like this. Well, we're thinking again about this problem of locomotion. In particular, we'll talk about this passive walking problem for now to put this sort of more high-dimensional actuated version aside. So think about this bottom left simulation. The kernel function that basically all of robotics ends up using with Gaussian process models is called the squared exponential kernel. And the reason is because it gives normally distributed rollouts over a horizon. So for example, with something like MPC, we start predicting forward the dynamics, and it's just normal distributions all the way down. There's a nice analytical exact posterior, which is obviously very, very attractive. The trouble is that this assumes that the underlying function that is being modeled is continuous, which is obviously not correct because dynamics are hybrid. So we asked, maybe is the softness somehow able to still have us do this continuous approximation? Maybe if we choose a reduced dimensional state where these discontinuities are maybe softer, what would that end up looking like? So what this kernel is, for some context for our very specific experiment, it again, you can imagine here, squared exponential is clear, but in the place of this, what we would have seen as a covariance matrix for a multidimensional Gaussian, we have what are called hyperparameters, these length scales that normalize the influence of different states on the prediction. So the task of optimizing these hyperparameters is the big step for choosing an appropriate kernel, the model selection problem. What the literature says is that if we are inappropriately selecting our model, for example, trying to model a discontinuous system with the squared exponential kernel, these LDs will be artificially small. These representative length scales will try to capture, discontinuities, very, very small time step, large changes in motion. So we went and explored that. Does this end up happening? Again, we took data from the simulation and performed a number of these non-convex optimization restarts of maximum likelihood estimation for what these hyperparameters are given our specific data set. So what we did, we performed about 800 of these and went and binned the results in terms of where the convex approximation ended up in terms of the local minima to see if there was a trend we could find for global. And the answer is that it actually looked pretty good for certain states. So this was predicting, for example, the X dimension. We're using here an approximation of this robot as a rolling disc. Again, something that maybe you can have intuition about it maybe being a little bit smoother than more of a walking model. And you can see here that there are obvious trends in hyperparameters for the length scales in the kinematic directions. The observation here is that these are on the size scale of the robot itself, meaning that they are not artificially small. We do possibly have the opposite problem. Large length scales indicate potentially underfitting for a Gaussian process regressor. So for example, you can see that the angles here are basically irrelevant in terms of the optimal hyperparameters and are excluded, or just predicted as noise, basically. And when we went and did a cross-validation test, we basically confirmed this. The GP predicts some kinematic states pretty well, but let's see if you all can actually see this. Hopefully my window isn't in the way. But other states it does not predict well. So some of these where you see about 100% error or so basically mean the GP predicts noise. Initial results suggest that this might be valid for kinematic directions, but maybe not others. And to go and address this, what we are doing, let's see if I can get these videos to run. And there we go. We're changing the robot first, actually, and changing the problem to reduce the hybrid, behaviors. If we learn sort of within one stepping motion of this particular three-legged robot, not only is this sort of a better robot for locomotion purposes, but we also potentially, don't have these hybrid phenomena. So that's where we're going with this. And thanks to my lab mates for all the assistance in this work.
Thank you, Andrew, for the really interesting talk. Are there any questions for Andrew from the audience?
So I was wondering if Andrew, if you So can you comment again on the choice of the kernel function? I did not understand how you selected it.
Sure, absolutely. So there's effectively two parts to this model selection problem. One is choosing the form of the kernel, and the other is optimizing its hyperparameters.
Yeah,
and they're different. The former is done basically on intuition or problem statement. So for example, one might look at the data, which we did, and see what kernels might be appropriate. There's a great book on this that has a bunch of plots that says, if the data look like this, here's a good kernel. Or in particular like this, we really had this idea of reinforcement learning, predictive control, etc., something over horizon in mind, which basically limited us to normally distributed posteriors, for which this is the obvious choice. The other part to it is that optimizing these hyperparameters has to be done based on data, which is an optimization problem. So one is intuition and the other is based on data.
Okay, great. Thank you.
Yeah, you're welcome.
Andrew, may I ask a question? Sorry, I interrupted you.
Please,
so you mentioned if we chose that base kernel function and the hyperparameter is wrong, I didn't get what will be the effect of choosing those wrong in the same slide. Basically, I think I missed that part. So as soon as we get either the hyperparameters wrong or the kernel shape completely wrong. Thank you.
Sure, absolutely. So it's effectively the same story. What happens if we perform the model selection wrong? It's the same story as any kind of machine learning problem, and so we can look out for the very, very traditional questions. Do we encounter cursive dimensionality? Do we encounter underfitting or overfitting? That type of thing. So the next slide, I think, actually, let me show the whole thing here. Let's see, hopefully, okay, I'll just move the window. So in this case, we encounter basically a very traditional learning issue where we have selected our kernel form based on assumptions that aren't really correct. So that then when we go and optimize the hyperparameters, the best ones that are found are effectively explaining the data as noise in certain dimensions, which is demonstrated by these extremely large length scales. So you can imagine, divide, this is 1 over this number, and when you're going and normalizing these predictions. So 1 over 6 million is obviously sort of eliminating that entire dimension from the prediction.
All right, great. Thank you so much, Andrew. There is another question in the chat, but I would suggest if you can reply directly on the chat.
Yes, thank you very much.
Thank you for your amazing talk. Let's try again with Fukbui. Fukbui, are you there? Yes. Please go ahead. We cannot hear you. So in that case,
I think you're muted.
Yes, he's muted.
Okay, sorry. Can you hear me now?
Yes.
Okay, sorry for the bad connection, and I come back now. I think everything okay. So now we'll talk about my current research title: Observer Design for Fabric Reinforced Inflatable Soft Robot. Here's my content. And okay, this is the soft robots in our project at the University of Tulsa, Oklahoma State. This is called the Fabric Reinforced Inflatable Soft Robot. As you can see, our robot is a curved chamber made of silicone with an inelastic fabric embedded longitudinally to reinforce one side of the robot. When inflated, the robot will bend and twist, so it can trace the curve in three-dimensional space, like in this video, and thanks to the natural position of this fabric. And the entire robot arm could be used to do some tasks, such as to scrape or push against its environment. Right? So in order to do future model-based control designs, our research team developed a new discrete model to represent our robot. This model can account for wrinkles and twists. In this approach, we discrete the chamber longitudinally into a sequence of NDs, and each connected to its neighbors on either side by a single inextensible tray, which represent the fabric reinforcement. Each disk is considered to be a rigid body, and the generalized coordinate will be defined with regard to three intermediate frames, including 5 generalized variables between frame I and I+1, showing in blue, red, and green, respectively. 5 rotations, including alpha I, beta I, gamma I, Ci, and Phi I's, and 1 translation along this tray will make the coordinate of this I align with the coordinate of this I+1. And the twisting of the robots is accounted by this gamma I. So by relying on some fictitious link and angle from alpha 1 to phi n-1, we can use Euler-Lagrange formulation to find the equation of motion in the form of a set of ODE. And then you can form the Lagrangian and take its derivative to find the equation of motion like this one. And by using a canonical momentum vector P, we can rewrite the above equation in the state space form like this one. M is the mathematics, partial L over partial Q is the derivative, partial derivative of the Lagrangian with respect to each generalized variable. Capital I Q's is the generalized force, and the last term is the contact force contribution. And because at each operating point, the robot has a different pose due to changing pressure, and the element of this equation motion are also changing. So in order to describe the robot to how this the entire range of motion, we divide the entire system into K subsystem to fix a sequence of operating point by evaluating the equation of motion as corresponding pressure and form a switch linear parameter variety LPV system like this one. This LPV system includes a set of subsystems that represent robots at different working pressures. And we can then design a set of observers for the LPV system. Each sub-observer is in this form to estimate the system state, including angular position, angular velocity, and generalized contact force. Why we need this observer? Because the system state and the contact force cannot be measured directly because they are fictitious. They can only be estimated by directly by this observer. And some results, we examine the performance of proposed observer on a model which include 4 disks and 3 trays. We choose operating point at 4 increasing pressures and form the equation of motion as these 4 points to create a 4 corresponding subsystem that representing the entire working range of the sub-robots in the form of a switched LPV system. And at first, we simulate the observer in estimating the angular position of the static robots. In this figure, each subsystem is illustrated by a different shading from bright to dark. We can see that the estimate are quickly converge to true values from their initial value at 0.5. And here is the convergence of the estimates of angular velocities, assuming that the robot is moving. There are some bias when switching between subsystems, right? But they are quickly decayed. You can see the estimates error are almost 0. And in this simulation, we assume the robot is in static pose at 3 psi, and at contact is applied after first 2 seconds and is removed after next 2 seconds. And the zero line contact force are assumed to be random values in the range -1 and 0 Newton meter. We can see the good estimates of the zero line contact force on those the red line. And we also check the observer in the following experiment. We attach 7 sensors of the polymer 3D tracker system on the body of the robot, as in these pictures. In order to update its whole shape when we are pumping the robot by the following input pressures, as in this figure. And this video shows the behavior of the soft robot. Yeah, it's bend and twist in 3D space. Okay, and on the figures on the right, blue lines are the position of these 7 points measured by the sensors. The red line are the estimates produced by my observer, and we can see that the position of the sensor are well estimated in this experiment. Okay, so the conclusion so far in this research, we can develop an LPV system based on this tray model to represent the fabric reinforced inflatable soft robot. And we also can design an observer to estimate this soft robot states and zero line contact force. The observer is of high importance because the robot state and contact force are difficult to be measured directly by sensors. And this work set up a foundation for our future model by closed loops control of a class of fabric reinforced inflatable soft robot. Okay, and this is the end of my presentation. Thank you for your listening.
Thank you, Phuc.
Yeah.
Are there any questions from the audience?
Yeah, I have one. I saw that if you can go back to the experiments, I see that yeah, they work very well, but the time scale it's pretty slow. Is there any reason for that? And did you try also with more faster varying data?
Actually, this experiment still not 100% real time because we still in our progress, and this is actually we collect the data from the sensor in a previous experiment, and then we put the real data into MATLAB and fit into our observer. So the observer is still not in real time, but the data is from the real experiment. So it's still in the progress.
Thank you.
Okay, thank you very much, Phuc. Now it's time for Joshua Fishman, and he will present a control and trajectory optimization for soft area manipulation.
All right. Hi, thanks so much.
Welcome.
So let's see. All right. You guys see my screen now, right? All right. So first, I'd like to say thanks so much for letting me move this presentation today. I really appreciate it. Flexibility there. So I'm Josh. I'm a master's student in the MIT Spark Lab, and I'm going to talk about using softness for the purposes of aerial manipulation. So first, I'm going to demo a video of our system. Most of what I'm going to present today is in simulation, for which we use the SOFA soft dynamics engine with the soft robotics plugin developed by the Defrost group. So our proposed system, which I'll skip a little bit in the video, but our proposed system consists of a standard quadrotor chassis with the landing gear, as you can see here, replaced by a tension actuated silicone soft gripper. And we are going to use the system to carry out dynamic aggressive manipulation of unknown objects in unknown environments. Our proposed system outperforms in simulation a standard rigid gripper and a more naive soft manipulation approach in grasping all sorts of object types. And so first, I realize I don't need to evangelize too much to this audience. We're going to talk a little bit about the specific advantages of softness in manipulation. First of these is that softness creates robustness to position errors in your manipulator. This is super important in aerial manipulation because the precision you get out of a quadrotor is much less than the precision you'd get out of something like a traditional robot arm. Next, in sort of the standard way, softness allows you to grasp heterogeneous irregular object shapes without explicitly tailoring their grasp to the shape of the object you're trying to pick up. And finally, again, useful for our case, softness affords some resistance to sort of collisions at high momentum. Now we're trying to pick up objects going at speeds, meters per second, and softness lets us grasp without transferring too much momentum either to the object or to the drone. Okay, so what goes into soft aerial manipulation? So our system is premised on decoupling, splitting the system into two subsystems, the quadrotor and the gripper, and implementing separate controllers and planner for each. The advantage of this is that it lets us use standard powerful techniques from soft robotics and aerospace robotics. Disadvantage is that now for each subsystem treats the other subsystem and the influence from it as a disturbance that needs to be compensated for. But it's pretty easy to do because due to the inherent morphological adaptability of the soft components, which affords some robustness to disturbances, as well as the availability of powerful, robust adaptive controllers for quadrotors. So typically, what we're trying to do is control the 6DOF quadrotor pose, position, orientation, and derivatives, as well as the nominally infinite dimensional soft gripper configuration and derivatives. To do so, we have the 4 propeller forces, as well as 8 independent tendon lengths, 1 for each side of each finger. Let's see a couple things in the chat. Oh, sorry, not relevant. Okay, so to control the soft gripper, we use a standard FEM planner developed by Professor Byrne at ETH Zurich. This involves a neo-Hookean material model for our silicone fingers, a tetrahedral mesh discretization, and we model the tendons as well as the attachment points as stiff springs. All of these components have an energy, which is really easy to calculate, as well as the derivative energy is really easy to calculate. And so for the forward kinematics, we can just compute an energy minimizing configuration analytically using Newton's method to sort of figure out, given the set of tendon lengths, what the final configuration is going to be. Now do the inverse kinematics to find the desired tendon length, which will give us a specific configuration. We also can analytically compute the gradient of the node configurations with respect to the tendon lengths. And we can take a step and recompute the gradient and sort of iteratively solve for the inverse kinematics. For all of this, the node configurations Y, because the quadrotor is attached to the gripper, so the gripper configuration is a function of the quadrotor position. And so for the purposes of tendon planning, we assume that the quadrotor attains whatever nominal trajectory we plan for it. For the quadrotor subsystem, we use a modern adaptive geometric controller. Planning, we actually plan trajectories in the Cartesian position output space, which we can do because of a property of the quadrotor called differential flatness that I can elaborate on afterward if anyone's interested. Specifically, we plan trajectories as minimum snap polynomials because the snap of your trajectory corresponds to your control effort. And we can show formally, even though we're using an adaptive controller, we can show formally that under specific conditions on the load and on the quadrotor, like symmetry, we can show that even a non-adaptive controller would stabilize this system. But for grasping, we don't want to have a symmetric load. We don't want to have all these conditions that are operating under, so we use an adaptive controller. Okay, so with these components, how do you actually do a grasp? So we plan tendon length specifically at 2 key instants in the grasp. First of this is the instant of approach, which is when the fingertips are first over the target's centroid, which is all we assume we know. We only assume we know the target of the centroid of the target, not shape or anything like that. So at this time of approach, we want the gripper configuration to be such that the area between the fingertips and the target is maximized. This maximally increases the chances of actually enveloping the target. And what we've seen is that if we can envelop the target, we can consistently grasp it. And then at the time of grasp, what we want to do is minimize the distance between the fingertips and the target centroid. Intuitively, it's pretty simple. It corresponds just to closing the gripper, bring the fingertips in as close as possible so that we can actually sort of close the deal on the envelopment that we were trying to achieve earlier. Now, up into and between these lengths, we just linearly interpolate the tendons. In addition, we linearly interpolate first from the initial lengths to the approach lengths at time approach, and then from time approach to time of grasp, we linearly interpolate from approach lengths to grasp lengths, and then we hold the lengths constant so we can hold on to the object. So in addition to being simple, this linear interpolation has the advantage of minimizing rapid changes in tendon lengths. And rapid changes in tendon lengths correspond to large local accelerations of the gripper, which are tough to model and risk perturbing the quadrature. And so in addition to being simple, this sort of linear interpolation scheme actually has a lot of advantages. And with this approach that I've laid out, we can achieve consistent grasps in simulation of a target object of various shapes at speeds up to 2 meters per second, so quite fast. And in the bottom video, really, I think, exemplifies the advantages of softness in our applications. First off, we're hitting this object at 2 meters per second, right? If you try this with a rigid gripper, it sort of goes all over the place, knocks the object all the way across the room. But here, we're not displacing the object too much, we're not knocking it over, and we're not destabilizing the quadrature. Secondly, you can really see the advantages of our sort of enveloping grasp plan, where our soft gripper does not close instantaneously, but because we plan a grasp to sort of try to maximally envelop the object, we're able to sort of slide the object along and close the gripper on it, even sort of compensating for the reduced speed of our soft gripper compared to maybe something rigid. Okay, so our system works in simulation. Ongoing work involves a real implementation of our soft barrel manipulation platform, as well as testing of this. And work here is still ongoing, and hopefully we will have something to report here soon. So that's all for me. Thanks so much. And any questions?
Thank you, Joshua. Thank you very much. You present a slightly different topic than others, so very much appreciated. Are there any questions from the audience? Perhaps I have a question. It looks like this approach, so it requires a predefined approach into the object from the drone. So for instance, I'm trying to imagine if other kind of configuration approaching from the back. So it looks like you have to approach laterally. Is it the case?
Yes, so we assume planarity for the purposes of planning here, and that's definitely something we're thinking about, because with our real testing, it's hard to ensure that they're sort of lined up in a planar way, so definitely we're thinking about that. But yeah, you're right, that's a limitation right now.
You are planning to overcome this limitation?
We're thinking about how. We don't have a specific plan yet. We're thinking about sort of, because we think right now this is a limitation actually not of our algorithmic approach, but our actually sort of physical set layout of the fingers. And so we're thinking about sort of moving away from that sort of strict landing gear replacement layout. But yeah.
That makes sense. Thank you very much, Joshua.
Thanks so much.
It's now time for our last abstract presentation from Wei-Cheng Wang. He will present a discrete geometric approach to simulation of soft robots.
Hello, everyone. Can everyone see my screen?
Yes.
Okay, let's go ahead. So I think, so let's get started. In the previous speaker, they mentioned some of my work, and here I'd like to focus on the physical-based simulation for the soft robots. So this work is a cooperation between University of California at Los Angeles and Carnegie Mellon University. In front of you is a soft rolling robot, and by actuating its limb in a specific sequence, this type of robot can move forward. So our purpose here is to make a numerical simulation to capture its dynamics. First of all, we need to characterize the mechanical response of a single actuator. We found that by actuating the material, its natural curvature and the relative stiffness would change as a function of time. We evaluate the beam and deflation as a function of time from both numerical simulation and experimental side to find the best fit. So the best fit is a piecewise function on the left corner. Secondly, we discretize the structure into multiple nodes and model the structure as a mass spring type system. Specifically, the total energy is the sum of the stretching and the bending energy. And the bending energy was calculated based on the curvature of the limb. By doing that, we can capture the geometrically nonlinear deformation of the structure. Then we need to consider the contact between the soft structure and the solid ground. We use the Coulomb frictional contact law to model the structure. There are three cases. For example, if the external force was negative, the node should not be constrained and it would take off. Otherwise, if the force was in the frictional zone, this node should be fully fixed. The last case it can slide along the tangential direction of the ground. Overall, we use a second order numeric-based time marching scheme to integrate the equations of motion for its momentum conservation. Here are the final results. First of all, we consider the most simple case, which is on the planar surface. On the top is from the experimental side, and on the bottom is from our numerical simulation. And secondly, we consider declined surface. Then we consider an opposite case, which is an inclined surface. If we increase the inclined angle to a specific number, the rolling robot can no longer move forward. Our numerical tool can also capture the nonlinear surface, the contact between the robot and a nonlinear case. For example, the sine curve. In this case, we start the robot at the top point. Finally, we use a single actuator as a jumper robot for demonstration. So overall, in all the cases, we found quantitative agreements between the desktop experiments and the novel numerical tool. Moreover, our numerical simulation can potentially run faster than real time, which means if we simulate a physical process like 10 seconds, our numerical tool would only cost something less than 10 seconds, say 3 or 4 seconds. That is very important for the online control for software robots. In conclusion, to simulate the dynamics of shape memory ally actuated software robots, we first characterize its mechanical response. Then we use a geometrically nonlinear model for the elasticity. Then a Coulomb frictional contact law was used to implicitly consider the contact. Next, we use a viscoelastic constitutive relation to perform the elastic and inelastic collision between the soft material and the solid ground. Finally, we use a numeric-based time marching scheme for the momentum conservation. Overall, our numerical tool is a robust, accurate, and effective framework, which can be potentially used for the optimize the design and trajectory control in software robots. So that's all my presentation. Thank you.
Thank you very much. Thank you very much for your presentation. Are there any questions from the audience? Okay, perhaps I have one question. So what about 3D locomotion or in general 3D simulation? Are you planning to go in this direction as well?
We are currently working for. So here we use a planar beam model for the 2D locomotion. In the future, we use a 3D plate and shear model for the 3D case. For now, we are currently working on a legged robot in 3D.
What are the main steps to reach this goal? So since you're using this discrete geometric approach, what's the biggest challenge?
can you pattern it? Can you repeat?
What are the biggest challenge to use the discrete geometric approach in 3D? I mean, what are the steps you plan to do to reach this goal?
So here, because the motion is in plane, so we use the planar beam model. In 3D case, we will use the plate and shear theory. But here, we can still use the plate and shear theory. It is unnecessary and time-consuming.
Okay, thank you very much, Wen Cheng, for your contribution today. So this was our last abstract presentation. I will remind you that during the panel discussion, we will award 3 of them with $200, kindly sponsored by Disney Research. Now it's time for Ian Walker. Unfortunately, Professor Walker cannot attend the live event. So unfortunately, there will not be question and answer for him today. You can address your question by email after the video. Professor Walker completed his PhD degree at University of Texas at Austin, and now is a full professor at Clemson University. His research is focused on novel continuous robots and soft robots inspired by tongue, trunk, and tentacles. Let me share now screen.
I'm Ian Walker, and I'm with Clemson University in South Carolina in the US. And I'm delighted to be part of the workshop today, the IROS workshop on application-oriented modeling and control of soft robots. And I'm just sorry it has to be a virtual workshop, and so we're not able to see each other in person. But I would like to thank the organizers for all the efforts they put in making it happen, particularly in these challenging situations that we have today. So I'm going to talk a little bit about Continuum robots, their modules, the modules that make them up, and some of the issues related to their control, which I hope will fit with the general theme of the workshop. So I'm going to talk about Continuum robots and the sense in which they are soft, and some of the potential that these structures provide, and some of the problems in making them work, particularly as related to their control. So Continuum robots, they're defined in a number of ways, but by and large, the general definition is that they have a continuous and compliant backbone. So a backbone that can move and be bent into different shapes all the way along the backbone. So in contrast to traditional rigid link manipulators, for example, where the links are rigid and they can't be bent into any other shape than they begin at. And so Continuum robots have no elbows, wrists, vertebrae. So in that sense, Continuum robots are more inspired by invertebrate structures in the natural world as opposed to vertebrate structures such as ourselves. And there are various motivations, but fundamentally the main motivation is to make use of the increased degrees of freedom in the system. In theory, there are an infinite number of degrees of freedom, although those are typically constrained in the way that the hardware is built, as we'll discuss as we go along. And what you generate at the end when you build one of these things is that you have some inherently compliant chunks or modules or sections, as we call them, typically for these systems. And so these are compliant, and in that sense, these robots are soft. So these modules, typically these sections, the top left image here shows 2 sections, one bending one way and one bending the other, in a tendon actuated device. And so each of these 2 sections has 2 degrees of freedom in bending, and that makes it a 4 degree of freedom device. The device on the top right, the octarm manipulator, which we'll see a few videos of later, has 3 sections, 2 that you can see quite easily and 1 that is back into the picture towards its base. And each of these sections that are pneumatically actuated are 3 degree of freedom sections, that they have the 2 degrees of freedom of bending, but also can extend and contract. So each section has a 3rd degree of freedom. And the tendril robot at the bottom has 3 sections. And so those sections have, again, 2 degrees of freedom in bending, and also can be controlled in terms of their extension and retraction. They're a concentric tube design that is spring-loaded. So As an example of an early continuum robot design that is a hybrid of some of these design techniques is something we call AirOctor that we designed about 15 years ago. And so it's a combination of remotely driven tendons and pneumatics, and I'll play a video. So here we can see it extend. It's basically a tube within tube structure. The white internal tube is pressurized, and that allows us to control the length and the stiffness of the device. And the outer tube has 3 tendons terminated at its tip. And by pulling differentially on those 3 tendons, we can control the bending of the structure. And so this gives us a basic element, a basic module. And so this is a section with 3 degrees of freedom, 1 in extension and 2 in bending. And if we take 2 of these sections and we put them together, then we can get the robot that we have, the version up there on the top right, which is a 6 degree of freedom continuum robot. So continuum robots can do cool and unique things, at least with respect to conventional rigid link robots, and that's their main motivation. And so I'll show several of those things in this video. So here's an example of the Octarm with a cover on it, picking up some traffic cones. And so until we did this demo, the order of 15 years ago, we'd not seen traffic cones, or at least not in the context of robotics. And so we were asked to see if we could manipulate those things. And novel manipulation in this fashion is one of the main motivations for continuum robots. We can wrap around using the structure and the compliance of the continuum robot, something we've never seen before, something that would be very difficult for a parallel jaw gripper, for example. And so that's one advantage, novel manipulation. Another often touted advantage potentially of continuum robots is novel navigation. So here we're navigating a tube structure. So the white tubes basically go straight down. As we look at it, they come straight towards us and then straight down again. So it's 2 90-degree bends. And we're navigating this purely with the mechanical abilities of the structure itself. There are no sensors involved here at all, apart from the tip cam, which we're seeing the footage of on the bottom left. And it is able to work its way through the end of the tube and see the Coke can that resides there. So again, novel navigation, and here in a way combining the two in water to find, restrain and retrieve a piece of wood. When we were doing this demonstration, we hadn't seen the piece of wood before. We had no idea we were going underwater until several minutes before this footage was taken, but we were still able to adapt to be able to constrain and then restrict and grab, and then be able to retrieve the piece of wood. And so these are the sorts of things that are potential big wins for robotics if continuum robots can be made to work nicely. But of course, to make it work, you have to control your inputs to the robot to get the robots to be able to do what you want them to do. And that's just not a given. So I'll show a video in a moment of one of our early prototypes, the first time we built one of these things. And so at that point, we looked at it and said, well, it looks very beautiful. Now, how do we make it work? And what you'll see is a video of us basically consecutively pumping air, it's a pneumatic robot, into the various actuators that we have to control the robot. And it comes with sound effects.
Okay.
So here's the initial problem that we are faced with in continuum robots and in soft robots in general, that you have a compliant structure and you have some actuators, but until you coordinate those actuators, then what you have is something that is hard to control and unpredictable until you're able to coordinate your actions. And so control of these soft and continuum structures is obviously very important. So here's the first thing that we did to try to control this device. So I'll play the video in a moment, and basically it's the same device, the Octarm being held vertically against a gravitational field, and the idea is to move the tip up so that it's pointing vertically. And so the two panels that you're going to see move, on the left it's without PID, just a proportional controller, simplest controller you can think of. And then on the right is a PID controller, which is more sophisticated and commonly used, but not in the scheme of things, the most sophisticated robot controller that one can use. And so I'll play it just to emphasize some of the inherent difficulties in controlling a structure with a lot of degrees of freedom and a fair amount of compliance in it, that it's not trivial. And so the PID is managing it. It's working a little bit, but it's managing it. But without the PID, just the proportional control, it's not working very well at all. And so here's an example of a simple controller that kind of works, but if you know anything about control, there are a lot more sophisticated things out there than simple PID controllers. And people have been working for quite a long time towards more sophisticated controllers, model-based controllers. So for quite a long time now, kinematic controllers have been basically established. So kinematics for Continuum robots works well if the particular physical hardware you have satisfies some reasonable assumptions. And the reasonable assumption usually made is that you have constant curvature, so that the energy that in each one of the sections, the modules, distributes it evenly, and then what you get is a constant curvature section or a chunk of a circle in space. And that makes the kinematics relatively straightforward to establish. And based upon that, you can do closed loop kinematic control of such devices, and it works reasonably well, but not perfectly. And so for quite a long time now, the idea of dynamics-based control, the obvious next step up, has been an active topic of research and continues to be as we speak. And so lots of different techniques and methodologies have been brought to play in dynamics-based control. They make different assumptions. There have been established in hardware to greater and lesser amounts, I would say. But basically, they all have to deal with the same underlying general issues. They're issues of complexity. How complicated is your model? How easy or not is it to work with? Can you use it in a closed form? Can you compute it in real time, et cetera, et cetera? And at core of that is the unmodeled dynamics. What have you left out? What assumptions have you made? And in making those assumptions, what things that exist in the real world of physics are not there? And so therefore, the theory that you're establishing, how well is that going to work? The images here are a copy of some of the pages of the calculations we did of the order of 15 years ago when we first started to work out dynamics, Lagrangian dynamics in this case, for a single section of one of our devices. And the number of terms is large. The complexity is sufficient that it's very hard to go through and check to make sure that you've got exactly the right set of terms without any typos, et cetera, et cetera. And I include that just to make the point that it can be quite complicated to work on model-based control of these kinds of structures. As an example of something that's a little different that we've been working on recently is the idea of using robot dynamics, but using more conventional robot dynamics to be able to address some of the issues in continuum robot control. So here, the basic idea is that we take a continuum robot section or sections as evidenced in the figure on the left. And so generally speaking, you model these things by the arc length S of the length, which may or may not be variable, and then the amount of curvature that it has, making the assumption here of constant curvature, and then taking that chunk of a circle and how is it rotated around with respect to its initial tangent in space. Those three variables typically are the way that the coordinates, the shape coordinates are parameterized. And what we chose to do in this particular case is to take a virtual robot, a virtual rigid link robot, which is on the right, which is a 4-link, although a 3 degree of freedom. Two of the joint variables are coupled. And we took a rigid link robot, a virtual robot, non-existent, but one that traces out the same kinematics. So basically you have an extension, which is basically the chord across the continuum section, and then the three rotational variables, I should say, are there to align the tangents and to make the curvature. And so two of them are identical to each other, theta 2 and theta 4. And what's the idea here? Well, the idea here is to realize the controller that the block diagram is given on the right. So basically the green stuff here is the actual Continuum robot hardware. And so basically we take the Octarm robot and we sense from it its shape. And then what we do is we feed that shape back into the red block. And so the red block is basically a controller, virtual controller of the rigid link system. And so therefore, in this particular case, we implemented an inverse dynamics controller, reasonably standard in the field. And so then the idea is that we do the control within the red box. And then when we produce the control torques for the virtual robot, then we have a torque to pneumatic pressure. Pneumatic pressure is the actual input to the Continuum robot. So we have a transformation between the two things. And what we do is we then control the Continuum robot, whose dynamics are much more complicated, with the controller based in the relatively simpler world of the rigid link system. And so we can apply this not just to one section, but to multiple sections. And so we used for the experiments the Octarm robot that we've seen several times so far. It's a 3-section system, and the feedback from it come from string encoders, and from string encoders and constant curvature kinematics, we can estimate the shape. And so basically that is fed back from the Octarm, and then it goes through the control in the virtual rigid link, a 2-section rigid link system, 2 of those things composed together in series. And then through the transformation, we go through the pressure regulators that are the inputs to the Octarm. And it works. So here's an example. I'll show the video in a moment. And so basically for a single section, what we're doing is we're asking the arc length, so the length to vary sinusoidally as we are the curvature. And then the orientation, how that circle is rotated in space, is basically going through a sawtooth, which is basically a rotation here, sawtooth in 2 pi. And it works. You will see it doing it. Works quite well for a single section. And it works for 2 sections too. So here of the 3 sections, we're not actuating the first, but the second 2 we are. And again, we're making step changes, or a step change with a ripple then with the tip section, and a step change in the length of the midsection. And then for the midsection curvature, we're making a step. And for the midsection, with the tip section curvature, we're having oscillations, and we're rotating around the midsection, but not the tip. So that's like this. And it works well. And it's a good example of instantiation of a controller. We can compare it with the PID control, and it works better than the PID, as one might expect, since it's a model-based controller. But is it more complicated? Is it as complicated as it needs to be? Well, it depends. So here's an example for the Octarm, again, using simple motion primitives. So here what we're doing is a simple hook and pull. So here's a PD control, no model-based anything here. So basically we're trying to wrap around this object. And essentially here the idea is we just make a hook and pull. And it works. And we can also do similar manipulations without any sensing. And basically, the idea here is that we're using much more strongly than we were before the physical characteristics, the materials, mechanical properties of the robot using its compliance to be able to do most of the work for us. So we're basically pushing ourselves in the right direction and letting the compliance of the robot do what we need to do. So simple and effective, relatively straightforward, but it works. And I think that leads us to a bigger question of some wider issues for Continuum robots in particular, and for soft robots in general. How much is enough control? You have this soft structure, how precisely can you control it? And then the other question is, how much do you need to control it? If you can do something effective with it with a simple controller, why do you need the more sophisticated controllers? When do you need the more sophisticated controllers? And the answer is it probably depends on the application. And biology suggests some simple solutions. The elephant's trunk has about 10,000 muscles in it, but it's certainly not thinking about 10,000 things when it moves. It's using motion primitives as we've seen before. So in summary, compliant Continuum modules and robots they need some form of control. And as designers and as people implementing those things, we make some choice among numerous options. And there are trade-offs. Some are more sophisticated and with some costs associated with that. Some are simpler. And the question is, well, a big part, I feel, at least, in what is the right thing to do is, what do you want to do with the device? If you're looking to do something very complicated with the device and you need reasonably high precision, then you probably need a sophisticated controller. On the other hand, soft robots and continuum robots, very often, they're not designed with high precision in mind, that they're designed with the idea that what you're going to do is you're going to use the very softness, the very reason for choosing a soft or a compliant device is to allow some slop, literally and figuratively, in how you interact with the environment and in what you do. And in that sense, maybe simpler controllers, controllers that are not based upon models at all, may be the way to go. And so that's an open question for the field, I think, as to what we want to do and what we judge to be good and what we judge to be effective. I think very much depends upon where we come from and what we are trying to achieve with the devices. So I'll leave that as an open question. And before I finish, I certainly would like to say thanks to the many people who have done the work that we've seen the results of here, and the sponsors who have made it possible. And with that, I'd like to thank you very much.
Okay, so as usual, very interesting talk from Professor Jan Walker. It would have been amazing to discuss with him all the idea he pushed forward. I hope there will be future chance for that. Now it's my pleasure to introduce the next speaker and the last of this section, Professor Isuru Godage. Isuru, are you here?
Yes, I'm here.
Hi, Isuru. Yes.
Hey, thank you for all the hard work that you put into making this workshop a reality.
Thank you, and thank you to all the organizer. So let me introduce you briefly. Professor Isuru completed his PhD from the Italian Institute of Technology and the University of Genova, and he's currently assistant professor and director of the Robotics and Medical Engineering Laboratory at DePaul University. His research interests include design, modeling, and control of continuum and soft robots. Today, Professor Isuru will discuss with us hybrid dynamics for variable length continuum arm. So Isuru, would you like me to play your video?
Yes, please. My name is Isuru Godage, and I am a faculty member at DePaul University. The topic of my talk today is hybrid dynamics for variable length multi-section continuum arms. What that means is that in this talk, we'll be learning how we can leverage certain properties of continuum arms such that we can approximate the behaviors of such system to equivalent rigid-bodied robots. By doing so, we are able to benefit from already mature and highly numerically efficient dynamic algorithms to derive sub-real-time dynamic models for variable length continuum arms. One of the key motivations for large-scale continuum arms is that they could be excellent co-robots in assembly lines and industrial settings. As you can see in this slide, at the moment, these rigid robots involved in these assembly lines are caged like animals. The reason is that they are inherently dangerous should they malfunction. As a result, they are kept separately. On the other hand, continuum arms, being inherently compliant, are therefore naturally safe to work or deploy alongside humans for achieving collaborative tasks. Here you can see how continuum arms can leverage their passive deformation and compliant operation to achieve unique objectives. For instance, on the left video, you can see a continuum arm navigate through a narrow channel in an object inspection operation. And this is a task that a rigid robot would fail. On the right side, you can see how these continuum arms achieve motion through structural deformation, whereas rigid robots use actuated joints. So this is one of the fundamental differences, and also a unique property that renders subsequent modeling stage a challenge. Considerable amount of research has been done on continuum arms over the years. The idea of continuum robots was first proposed in late 70s, and since then many researchers has tackled the problems of how to design continuum robots using various actuators and design methodologies. Also, the work involved various forms of kinematic modeling, path planning, inverse kinematics, so on and so forth. Specifically related to the topic that I'm doing today, I list a few of many researchers who has contributed significantly to the field of dynamics modeling of continuum arms. Before talk about modeling, I thought it would be better to refresh our understanding of how these continuum arms are made. The particular type of continuum arms that I'm focusing on today are called pneumatically actuated multi-section continuum arms. To make these continuum arms, you need to first learn how to make a continuum section. To do that, we use 3 pneumatical muscle actuators, bundle these together to create a section, and then we stack, in this case 3 together, to create a multi-section continuum arm. And when you change the length of all these 3 muscle actuators simultaneously, then you get PO extension or contraction if you use contracting muscle actuators. But if you change the lengths not at the same amount, then you get this differential length change, which causes certain sections to bend. And by combining the bending amount and direction of individual sections, then you can generate these organic looking elephant trunk like motions. In this slide, we focus on the kinematic modeling of continuum arms. One feature that we are going to use in this development is that each of these sections are kinematically independent. That means the deformation of a section does not kinematically affect the other sections. And this is different from tendon actuated continuum designs, where the tendon, since it routes along the length, can affect the overall deformation. But in this case, it does not. So in order for us to model the entire arm, we only have to model a continuum section. And if we know how to model a continuum section, then we can use the coordinates transformations to come up with the model of the entire arm. To do that, we first consider a single section. Because of the way it is constructed, the length change causes it to bend in a circular arc shape, and we can characterize this arc shape by 3 coparameters, which we can then use to derive the homogeneous transformation matrix. And once you know that, you can stack these together to derive the model of the entire arm. This circular arc assumption is a very reasonable assumption, even though not perfectly. Here you can see in this figure, this arm is, hanging in the influence of gravity, but still it maintains this circular arc shape deformation, which we're going to leverage to our development of the dynamic model later on. Before we talk about the hybrid dynamics modeling, let us first take a look at the steps involved in getting there. First, we are learning about the integral Lagrangian approach. In this case, what we do is we first consider a single section, like in the case of kinematic modeling, and then we assume a thin disk in this continuum section. We derive the mass for that and the velocities associated to derive the kinetic energy and the potential energy. Then by integrating it along the length of this section, we can find the total kinetic and potential energy. We then combine the kinetic and potential energies of all these continuum sections, then apply Lagrangian operations to derive the equations of motion. The integral Lagrangian approach consists of many integrations. To increase the computational efficiency, we used pre-computed integrals and then proposed a recursive framework to compute the equations of motion. And this allowed us to develop models, as you can see in this video, a 10-section continuum arms, that means 30 degrees of freedom. And this method allowed us to seamlessly scale this approach. And also, we used model kinematics to derive the dynamics. Model kinematics, what it does is actually convert these numerically unstable forms to polynomial forms, which are significantly stable and numerically efficient. The integral Lagrangian approach allowed us to model the dynamics of a 3-section arm and run the dynamic simulation in near real time. Further improvements were then proposed using a center of gravity-based approach. In this approach, the fundamental idea is, can we leverage the approach used in rigid body robots, whereas each link has their center of gravity, and what they do is they derive the dynamics at a frame in the center of gravity such that it simplifies the dynamics. The approach, if exists, would then consider a continuum arm and try to derive the dynamics based on its behavior of the center of gravity. But the problem is, unlike rigid robots, the continuum sections deform. That means the location of the center of gravity changes as it deforms. On the other hand, these continuum arms extend or contract. So these are like significant challenges to realize this type of approach. To test whether such a center of gravity approach possible for continuum arms, we did some tests here. We first modeled a lumped system for continuum arms using these distributed masses along the center line. And then we created another model where we derived the dynamics using the center of gravity of the arm. And then we tested how the system energy changes. And as you can see in this plot, the lumped model handily beat the center of gravity model because the lumped models, when you have 3 masses, distributed masses, it outperformed the center of gravity model. But you can see the center of gravity model approximates the energy, but it remains constant. That means we can introduce some sort of a scaling factor such that we can make it more accurate, try to approximate the overall system energy better. Once you introduce these scalars, you can see now the center of gravity-based approach can approximate the system energy better than a system with 22 distributed masses. And this all by using or writing the equations for a single mass instead of 22 different masses. This significantly increased the numerical efficiency as well as the numerical stability of the system. And when we tested, you can see the dynamic response is on par with the integral Lagrangian approach. You can see it here clearly though, but this red line is the center of gravity approach and this dotted line is the integral Lagrangian approach, but they are essentially on top of each other. And this proved us that a center of gravity based approach in fact can work. Having derived the center of gravity approach for a single section continuum robot, next challenge we have is whether we can extend the same approach for multi-section continuum arms. To do that, we need to address 2 problems. The first one being the continuum section of a multi-section continuum arm has a moving base. That means the system could have a kinetic energy even though that particular section is not actuating. And this motion is due to the motion of preceding sections. And this is a problem because the earlier implementation of a center of gravity model, we did not include the rotational kinetic energy. But this is a problem for multi-section continuum arms case. To solve this problem, we consider a disk of radius r and m at the center of gravity. This allows us to incorporate both linear and angular kinetic energy in the derivations. Once you do that, we can find the difference between the angular kinetic energies of the two systems and find that there are these terms that does not cancel each other. To make them cancel each other, we introduce these energy shaping coefficients. And then we do that same for the linear kinetic energy case. This allows us to formulate this the energy difference as and constrained optimization problems where we find these energy shaping coefficients such that the difference between the two systems is a zero. When we do the computations for large number of data, we find that there is in fact scalars that matches this energy. For example, here you can see one such term and one such coefficient, how it matches this energy very well. This was statistically observed for 10 million points, and it matches very well overall. And once we find these kinetic energy shaping coefficients, we can use it to derive the total kinetic energy of the system and then formulate a recursive dynamic equation algorithm, much like the integral Lagrangian case, to derive the equations of motions. Once you do that, you see that it results in a scalable system, and it significantly outperforms the integral Lagrangian method. Here you can see how it scales up against number of sections, and in the bottom figure you can see the amount of performance increase with respect to the integral Lagrangian system. For a 3-section arm, we observe 6 to 8 times a performance increase, but when you have more section, it has even higher performance increase. And the MATLAB implementation of the algorithm gets us 9.5 kilohertz step execution rate, which resulted in 6 to 8 times faster than real-time simulation. The center of gravity derivation proved us that we can use this lumped parametric approach in an energy-conscious way to derive dynamics for continually deforming bodies. To test this idea, what we were trying to do is to see if we can introduce a new set of joint parameters such that it would describe the motion of the center of gravity as the continuum section move. If we do that, then we can in fact use rigid-bodied algorithms to derive the dynamics. But the problem in the center of gravity approach is that we had to use these energy shaping coefficients. This energy shaping coefficient works for integral Lagrangian approach, but for rigid-bodied algorithm, it typically uses these velocities and then force balance in two passes. And there's no way we can use energy shaping there. To solve this, we consider a disk of mass m and radius r along the length of the arm. The idea is to see if we can find the optimal placement of this disk such that it approximates the energy of the entire system. And if we have such a solution, then we can use that idea to propose this rigid bodied equivalent system to derive the dynamics of a continuum section. To test this idea, similar to the previous constant optimization method, we describe the energy of the system using integral Lagrangian system, and then we derive the energy of the lumped model and then optimized for the optimal placement of this disk such that the energy of the two systems match. And when you do the statistical verification, you find that at psi equal 0.6, it matches the system energy overall. Having found an optimal mass placement without energy shaping coefficient, we can propose a new rigid body equivalent system with a separate set of curve parameters to describe the motion of the center of gravity. Once you do that, you can use this joint description in terms of revolute joints and prismatic joints to describe the motion. By doing, we can make use of rigid body dynamic algorithms to derive the equations of motion. But the problem that we need to solve before that is the continuum arms have these length parameters that describes its joint space. But this rigid model that we propose have independent set of joint parameters. In order for us to truly come up with a model that is useful, we need to have this mapping between the two, and which can be done easily using the existing coparameters to these rigid body mobiles. Once you have that mapping, we can implement the dynamics algorithm as shown in this diagram. What we do here is we take the joint space velocities and displacements from the continuum section, namely the length changes, then convert it into a rigid bodied system joint space parameters, and then use the composite rigid body dynamic algorithm to find the joint space accelerations, and using the inverse relationship convert it back to length parameters, in this case length velocities and acceleration. By implementing this framework, we can calculate the dynamics of multi-section continuum arms significantly faster than the center of gravity approach. We then tested the numerical efficiency of the proposed hybrid system. The overall algorithm is of O(n) squared complexity, but it runs at 20 kilohertz for a 3-section arm, twice as fast as the center of gravity approach. On the right side, you can see the performance increase with respect to the integral Lagrangian approach. And for a 3-section arm, it gives us around 12 times as fast. That translates to about 20 times faster than real-time execution. And the results generated from the proposed system closely matches to that of the integral Lagrangian approach, and we didn't see any discrepancy between the two results that describe the motion of the actual arm in the experiments. That brings us to the end of this presentation. In this talk, we talked about a new hybrid approach where we can use an equivalent rigid body system that were developed using energy techniques without compromising the accuracy, and use those and leverage efficient rigid body algorithms to derive significantly faster, stable dynamics algorithms that we can use for fast simulations and future control implementations. And with that, I'd like to thank you for your kind attention. And from here, I would like to take any questions you might have. Thank you.
Thank you so much, Isuru, for the amazing presentation. We are now ready for taking questions for Isuru. Are there any questions from the audience? Yes. Hadi, I think Hadi, you can speak up and ask your question directly.
Yeah, sure. Thank you, Isuru. Very interesting talk. Would you explain a bit more about your specific way of implementing Lagrangian dynamics via your polynomial basis approach?
So you are referring to the integral Lagrangian approach?
Yes.
Okay, it's quite simple, in fact. You consider this section is made of like a lot of thin disks, right? If we are using this parameter psi, right, to scale and find a moving coordinate system. So let's say psi is 0, then it's at the base, and if it's 1, it's at the tip. Then you can use this delta psi parameter to get a thin, like a length along this length. So that equivalent to having a disk. Then you write your energy equations, right? The velocity. Using the linear velocity, you can derive the energy for a linear kinetic energy for disk and the rotational energy for this disk, and then integrate along the length. That means integrate with respect to a psi. The delta psi becomes a d psi in this case. You can symbolically do that, and then you'll have the complete system energy. Then you apply the Lagrangian operation to derive the equations of motion.
Thanks.
Yeah.
Yes, very, very impressive, Isuru. What kind of controller you would like to implement with this kind of fast dynamics? I think if well understood, so that's your objective.
Yeah, thank you for that question. I mean, that is actually what we are working on. And now we don't have a problem with the dynamics modeling and how fast it runs. And then we have a model that can be used. I think the bottleneck right now is how we can control these muscle actuators fast enough to mitigate the ill effects. In the sense, there's a rate at which we can control the muscle actuators. So far, the motions that we can generate has to be like pretty slow than what we would like to do. Still, it performs better than the kinematic control for sure. But this is what we're working on right now. We are trying to come up with an arm that does not use pneumatic muscles, rather use maybe a predictable type of actuation, electromechanical actuation. This is what we are looking at. So if that is the case, then perhaps we can make the full use of these type of dynamic models for more, impressive looking controllers.
Great. Thank you so much, Isuru. There is another question in the chat from Christian. I would suggest if you can reply directly on the chat in the interest of time. Thank you again.
All right. Thank you.
So this closes this first part of today's workshop. We are right at the end of the break. So I would suggest to have at least a 5 minutes break for everyone and then come back at exactly 44 for Pierre, Professor Dupont talks. Thank you very much and see you soon.
Hi everyone. It is sharp 3:45 here in London. So I assume we can start. I see Pierre is there, smiling, ready to take the answers after the taking the questions after the presentation. I'm gonna briefly introduce Pierre. Pierre Dupont is Chief of Pediatric Cardiac Bioengineering and holder of the Edward P. Maron Chair at Boston Children's Hospital. He is also a professor of surgery at Harvard Medical School. His research group develops robotic instrumentation and imaging technology for medical applications. He's an IEEE fellow, a senior editor for the IEEE Transactional Robotics, and a member of the advisory board for Science Robotics. Pierre is going to present personalized stent and robotic balloon endoscopes for airway management today. Pierre, do you have anything to say before I run your video?
Well, thanks for that introduction, Hadi. I just want to say, you know, we've heard some great talks on modeling yesterday, today. We'll hear a few more. When I was putting this talk together in a 20-minute time frame, the question was this an opportunity to sort of focus on applications where, as engineers, we just love models for their own sake. And so I thought it might be good to focus on the applications here. So there's modeling behind the work, but really what I'm showing to you today in the video is the applications. So I hope you find that of interest, and Hadi, if you could start my video. Thank you.
Great, thank you so much.
Federico and the other workshop organizers for persevering in putting this workshop together, and also for including me. The work I'm presenting today arose out of an NIH grant on airway management, and it's really the first work I've done on soft robotics, so I'm honored to be included in a group of invited speakers. Let me jump into the motivation for our work. There are a variety of diseases in which the airways become blocked or need additional support in order to remain open. In some cases, all that needs to be done is for the airway to be dilated, that's expanded with a balloon, and then it remains open on its own. In other cases, a stent is needed to keep the airway open, and I've given 3 examples here. The case on the left is called tracheobronchomalacia, and it's a situation where the airway is floppy and it remains wide open during inhalation, but it collapses during exhalation. And this is a case where a stent is needed to keep the airway open. In the middle case that I've depicted here is the case of lung transplants, where at the anastomosis between the old airways and the new lungs, the airways can become occluded and multiple balloon dilations are often needed to keep those anastomoses open. And on the right is a case of chronic sinusitis, where the sinuses can become blocked and balloon dilation is needed to get them open. There are 2 major challenges to the balloon dilation and the endoscopic stent placement procedures. The first is the shape and the inner diameter of the airways can vary considerably between patients, and this is what I'm showing on the left. So fitting a standard size stent to a patient with a non-standard airway is sometimes not really possible. And the second challenge, as shown on the right, is that imaging is not typically integrated directly into the balloon and the stent delivery devices. So for example, in the sinus procedure shown here, the balloon is inserted in front of the endoscope. So the balloon and its deployment device tend to block the view of the endoscope, and it makes it difficult to precisely position the balloon in the sinuses. And one trick that's shown in this image in the upper right is to incorporate an optical fiber into the balloon. And the clinician looks for the glowing red light coming from the patient's forehead to figure out where in the sinuses the balloon is located. So I'm going to explain to you 2 technologies that we've been developing to address these challenges in airway management. The first is an approach for producing personalized stents for every patient. And the second technology is a robotic endoscope that can be used for diagnosis, stent delivery, and for balloon dilation. So I'll first concentrate on the project on the left, which is the personalized stents, and then I'll come back and describe the robot balloon endoscope. So looking at the personalized stents, there's two main approaches that have been used to create personalized stents, and I've shown these here. One is a hand-sewn approach. I call it the Frankenstein approach, where a clinician will cut up and sew together various stents to get the approximate shape they need. And the second approach uses 3D printing to create a truly personalized stent. And this involves taking images of the patient's airway, segmenting the images, 3D printing mold. The mold's then used to cast the silicone stent as shown here, and the entire process takes a few days and is a little bit costly. And our approach, as shown on the bottom left, is to customize the shape of the stent as it's delivered into the airway. So the stent is flexible, it's filled with a UV curable polymer, and it's impressed against the balloons of the airway walls by balloon inflation. And then an optical fiber inside the balloon cures the stent to the shape of the airway. We use a helical stent geometry that's based on a non-adjustable nickel titanium stent design that we previously developed. And I don't have time to cover the details today, but that metal helical stent design and delivery and removal tools offer a lot of advantages over existing airway stents. So they're a big improvement there, but they don't provide a personalized fit. So our goal here is to take that design and to turn it into a custom fit device. So let me explain the concept of the personalized stent in a little more detail. The stent is made of polymer tubing filled with a liquid UV curable polymer. It's delivered over a balloon, and I'm showing the steps and also a video of the delivery process here. So in order to preload the stent against the wall of the airway, the balloon is inflated so as to stretch the inner diameter of the airway by about 2 millimeters. And once the balloon is inflated to the proper diameter, an optical fiber is inserted through the lumen of the balloon to deliver the UV light. The liquid stent core is then cured, and depending on the length of the stent, the optical fiber may be moved to several positions to achieve complete curing. Curing time has to either be sufficiently short to occur during a breath hold, or the catheter lumen has to be used for respiration. And at the end, the balloon's deflated and the catheter is retracted, leaving the stent in place. Now, the design of in vivo stent molding involves 4 components. The balloon on which the stent is delivered, selection of the tubing and the UV curable polymer, comprising the stent, and the design of the optical fiber and curing strategy. And I really don't have time to cover all of these in detail, but I've listed a few of the requirements for each. The balloon stiffness has to be sufficient to expand the stent, but also to conform to the varying cross-section of the airway. It also has to be UV transparent and have a lumen for the optical fiber and for respiration during curing. And we shape set the tubing as a helix. So the tubing itself, we choose to be a UV transparent thermoplastic. And for the UV curable polymer, we searched for one that had high stiffness, cured fast, and also did not creep, which was a big challenge. So for the optical fiber, we ended up using a flat polished face that produces a flashlight beam irradiation pattern. And we characterized the exposure time versus the cured stent length. And based on all of these choices, let me just focus on showing you some of our application results. So often it's desirable to have a stent extend from the trachea into one or both bronchi. And so this is typically done with a standard silicone stent that looks like a Y configuration, as I've shown on the top left. But since these aren't custom designed, one could use the 2 other approaches I mentioned earlier. One is to cut up a number of stents and sew them together, and the other is an image-based 3D printed mold to create a true custom stent. So in our case, as shown on the right, we combined 2 of our helical stents, as shown on the right, and created a simple trachea bronchi phantom model, as shown in the middle right. And after inserting the stent into the phantom, we cured each branch separately, starting with the tracheal branch, so that each is customized to the diameter of that branch. And while the airway phantom we show here does not have a really crazy shape, I think it conveys the idea of how we can achieve a custom fit. As a second example of personalization, we looked at airways that have an hourglass shape. So currently, balloon expandable stents, rather than supraelastic stents, are used to produce variations in diameter along the stent. So in the case shown on the left, the clinician would take the stent off its delivery balloon, tie suture around the balloon as shown, and then place the stent back on the balloon. The suture prevents the middle of the balloon from inflating, and so produces an hourglass-shaped stent, as shown on the bottom, The problem with using balloon expandable stents, where the balloon deforms the metal of the stent to take on the desired shape, is that in the airways, when you cough, your airways contract. So your airways act as an anti-balloon and end up compressing the stent and making it loose. So as shown on the right side of the slide, our approach can produce a custom fit for an hourglass-shaped airway without any extra steps. The balloon expands along its length to match the radial dimensions of the airway, and the stent is cured in the shape. And while I don't show it here, we've simulated the airway contraction of a cough by applying compressive displacements about 3 times as large as our maximum anticipated steady state compression, and the stent behaved elastically. So we don't think we'd have any problems with stent recompression as is currently experienced with the balloon expandable stents. Finally, we also performed an animal trial in a 15-kilogram pig. Delivery was challenging because we were anticipating that the animal would be able to breathe using the airway space around the delivery cannula, but you never know exactly how big your pig is going to turn out to be. And as it turned out, the cannula filled almost all of the tracheal cross-section of the animal. So we had to perform insertion and curing during 1 breath hold, which was longer than we would have liked, but the animal did well through the placement procedure. And you can see the stent on the X-ray image on the left, and also in the endoscopic video on the right, that it's the stent is successfully preloaded against the tracheal wall. The animal was kept alive for a week, and the stent remained in place, and the animal tolerated it very well. So this was the personalized stents. And now let me jump to describing our work on the robot balloon endoscope. So this is the second challenge of airway management, namely that of the difficulty of visualization. So when attempting to look around corners in the sinuses, when attempting to deploy a stent, and also when positioning a balloon for dilation, the balloon blocks the view of the endoscope because they're separate instruments. So to address all of these challenges, we created a robotic balloon endoscope as shown on the right side of the slide. The easiest way to explain how it works is to see it in action. So here are 2 videos. One shows it walking inside a tube by alternately bracing balloons at its proximal and distal ends against the tube walls. And the middle section of the robot is comprised of 3 propulsion balloons that expand and contract linearly. These balloons produce a forward and backward motion and also enable the robot to turn, as shown in the second video. A small camera and LED are mounted on the robot's distal tip. So the balloons are inflated and deflated through small tubes that trail behind the robot. And the design is scalable, so that could be used both in the nasal passages and the lungs. And we also wanted to include a central lumen going through the robot for respiration, drainage, and to insert an optical fiber for stent curing. Prior robots of this type, the ones we saw, were typically very slow. So we want to make sure that we could move as fast as a clinician would typically move an endoscope. We also wanted to make the robots cheap and disposable, and we were powering them off of the wall pressurized air and vacuum sources that you typically find in a procedure room. So the pressurized air and vacuum to inflate and deflate the balloons, as I mentioned, is under control of microprocessor, and we programmed a video game controller to control both individual balloons as well as coordinated inflation and deflation to produce walking and turning motions. A standard 6-step walking sequence is shown in the bottom half of the slide, and starting with all 5 balloons inflated. The first step is to deflate the proximal anchor balloon. Next, the middle 3 propulsion balloons are deflated. Then the proximal anchor balloon is inflated, and so on. And in the next slides, I'll show you how we designed and fabricated these balloons, and also how we optimized them for enhancing locomotion speed and for turning angle. Since we wanted the robot to have a central lumen, the bracing balloons are built around a section of plastic tubing, as shown in the image on the left. A smaller inflation tube runs adjacent to the central tube into the balloon. And the balloon is formed by creating a cylinder from film stock. This is the film stock that's sold for air pillow packaging material. And the cylinder seam is sealed using a heat press and turned inside out. And the ends of the cylinder are folded using a pleating pattern that my former postdoc, Ying-Tang Li, developed, and they're glued as shown in figure D. I was really amazed when he showed me how he pulled that off. Excuse me. So while the bracing balloons are designed to expand radially, the propulsion balloons are intended to expand and contract axially. So we designed these as sealed cylinders with an internal helical stent designed to prevent radial collapse while being very flexible axially. And we found that it was possible to optimize the pitch of the stent. And I'll show you this on the next slide. Without the internal stent, when the vacuum is applied, the balloon collapses radially rather than compressing axially. So just like with our airway stents, the pitch has to be chosen small enough so that the balloon doesn't collapse between the coils. On the other hand, the minimum axial length of the balloon is the compressed length of the helical spring. So the optimal solution corresponds to having the balloon collapse radially between the coils just as the spring becomes fully compressed. So as an approximation, this occurs, and I've labeled this in the gold labeling on the left there. As an approximation, this occurs when the pitch of the helix equals the diameter of the balloon. This condition, as I've shown you here, is validated by the photos on the right. So for example, when the pitch is equal twice the diameter, the balloon collapses radially with a little axial contraction. And in the middle, when the pitch equals the diameter, the balloon collapses axially to the length of the compressed spring, as shown in the bottom there. Now you can use even smaller values of pitch, for example, half the diameter is shown on the right, and the balloon also collapses to the length of the compressed spring, but now the length of the compressed spring is longer, and so you've lost some stroke length as a result. It's possible to increase the robot speed by increasing the length of the propulsion balloons, but this also makes it harder for the robot to turn tight corners. It turns out that the biggest time component of the locomotion, inflation, and deflation sequence is the inflation of the bracing balloons. So a better way to increase the speed is by not fully inflating the bracing balloons over the six-step walking cycle. The price you pay, though, is that the traction force falls as inflation time is decreased, resulting in some slipping. So the plot on the left shows how walking speed varies with bracing balloon inflation time for 3 different walking environments. So the fastest speeds of about 7 millimeters per second are attained in a dry tube with an inflation time of a little over 0.3 seconds. But then when we added a lubricant to the tubes, we used mineral oil, the maximum speed fell to 4 millimeters a second, as shown by an orange curve. And walking in an ex vivo swine trachea, as shown in the bottom right, yielded the slowest speed. It was a maximum speed of about 2.5 millimeters per second. And still 2.5 millimeters per second is very close to what we wanted for typical endoscope advancement speed, so I think we're doing okay on that. Notice that the maximum speeds in the lubricated tube in the ex vivo trachea require longer inflation times in order to reduce slipping. Okay, so now to evaluate the capability of the robot in exploring the sinuses, we created an oversized model of the sinuses as shown on the right. It's really bigger than we needed to make. And we made, also I should point out, we made this video a little while ago, so it's not the most recent version of the robot. But what you can see on the left is the endoscopic view that corresponds to what you see at the tip of the robot as it's moving through the sinuses, and the little numbers correspond to those 2 videos. The robot velocities that we showed you on an earlier slide are quite appropriate for these procedures. And our maximum turning angle for the robot is 87 degrees, which will get us everywhere except into the maxillary sinus. So we're doing pretty well for that. Now let me show you a simulated balloon sinuplasty. So balloon dilation, as I mentioned earlier, is used to treat chronic sinusitis, and it's a very effective treatment. Some of the challenges, though, are that the endoscope is inserted behind the balloon, as shown on the left. So the clinician is not able to see inside the sinuses to examine whether the tissue, nor can they clearly see the balloon position. So by integrating the endoscope into the robot balloon, we're able to see into the sinus passages and also to see if we position the balloon sufficiently far into the passage to ensure proper dilation. So in the experiment here, we've modeled the sinus blockage using small balloons that the robot must compress. Now let me show you another example where we're using a robot to deliver a stent into a phantom trachea. Stent delivery is challenging because the robot has to be at least as long as the stent. And while it would be tempting for the robot to carry the stent over its middle section, the propulsion balloons do not expand radially as is required for in vivo molding. So the approach we took for this demonstration was for the robot to carry the stent on its proximal bracing balloon. We would have preferred to place it on the distal segment so the robot would not have to walk back through the cured stent, but this would have forced us to use a longer distal balloon, which would produce a larger turning radius. So the video shows the stent being delivered and cured inside our phantom trachea, and the process is identical to how we did it with a handheld stent. Once in position, the proximal balloon is inflated sufficiently to stretch the trachea and create preloading in the uncured stent, and then the stent is cured and the proximal balloon is deflated, and the robot carefully moves back out of the stent. Let me show you one more experiment here in which we used ex vivo trachea and lungs for a 40-kilogram pig. The robot was introduced into the trachea and we navigated into the caudal lobe bronchi. And this is as far as one would need to go for the typical balloon dilation procedures in the case of lung transplantation. The photos on the left show the sequence of views that start inside the trachea and then reach into the right and left caudal bronchi. And the video on the right shows the robot moving to and into the bronchi. You can observe that the robot's view rotates as the robot moves. This is because the propulsion balloon twists a little as they expand and contract. We were quite pleased at how the robot performed in this experiment. Let me just summarize now. The goal of the work I described today was to address two current challenges in airway management. We've developed an in vivo molding technique enabling every patient to get a personalized stent, and the technique is adaptable to airways of many different sizes and does not suffer the limitations of balloon expandable stents. The second project I described was a robotic balloon endoscope, and our goal was to address the imaging limitations experienced in balloon dilation stenting procedures. And we demonstrated the potential of the technology for use in both the sinuses and the lungs. So thanks for listening to me today, and I'd like to emphasize the work that I've described as the product of the hard work of my talented coworkers, who I show here. Roberta Miali from the University of Pisa is really responsible for the bulk of the work on the in vivo stent molding project, and Yingtian Li, my former postdoc, helped her with that, and also is the primary person responsible for the balloon endoscope. And I've mentioned my clinical collaborators, Drs. Rabar, Visner, and Jennings, who helped keep us real as we got through the project. So thanks very much for listening to me today.
Very good. Now we can have audience questions. I see we have one. So I'm going to read it aloud for everyone to hear as well. Very interesting work. I have a question about your helical stent. You mentioned that the airway contracts during coughs. Have you investigated whether the end of the helix scratches or otherwise irritates the airway when this happens?
That's a good question. We've actually done quite a few animal tests with metal versions of these stents, which are a little bit stiffer than the polymer ones. And we found that there was really no abrasion or irritation due to those stents. So we anticipate the polymer ones would be even easier on the airway. But it's a good question. It's kind of one of those important things that you need to worry about when you're dealing with live beings.
Okay, guys, you can unmute and ask, or just post in the chat box.
Well, while people are thinking of questions, let me just make a plug for my lab. I'm looking to hire a few postdocs about April on intracardiac catheter work. So we're looking at valve repair. So we have Continuum robot catheters with soft tool tips for performing valve repair. So it's really exciting stuff, real applications. If anyone's interested, feel free to contact me offline.
Great. Another prize for attendees to this workshop is the advertisement. Okay, I have a question actually. Given the theme of the workshop, what are the modeling requirements and control requirements of medical robotic intervention in a way that you're doing it? let me give some examples. Like, do you care about vibration? Do you care about forces on the robots along the way inside the body? Do you care about dynamics?
Yeah, no, those are really good questions, and let me address them in the context of catheter-based procedures. The being inside the vessels or inside the heart, there's, especially inside the heart, there's large motions from the blood flow and from the cardiac tissue itself. And those dominate any dynamic vibrations of the system. Now, certainly some people in the past have tried to, actively compensate for heart motion, and I think that's a dangerous idea. So from that point of view, the dynamic modeling isn't so important. You mentioned the other aspect of, deformation due to contact, and that's important, but it can be very complicated in the sense that there are so many contacts along the length of a catheter that you almost need to sort of decide, well, I'm not going to, worry about modeling this part. I really need to focus on modeling, say, the distal part that's inside the interior of the heart. So it becomes a very selective game in deciding, what to model and what not to model.
Thank you so much. We have a question from Ali. What pressures are used?
Oh, I think you're talking about the balloon endoscope. So I believe we were using a 5 psi positive pressure, and then whatever the wall vacuum value was at a negative pressure. So we certainly could have optimized those better. We were somewhat constrained by the quality of the regulators that we had available.
Great. With that, we thank Pierre for the interesting presentation and discussion afterwards. We're going to have him for the panel discussion, hopefully. So keep formulating your questions. The next talk, thank you, Pierre. The next talk is by Calibrating. I hope he's around, but I'm going to briefly introduce him. Calibrating is currently an associate professor of mechanical engineering with the University of Tennessee, where he directs the robotics, engineering, and continuum mechanics in healthcare laboratory. Dr. Rocker was a recipient of the NSF Career Award in 2017, and he currently serves as an associate editor for the IEEE Transactional Robotics. His research interests include modeling, design, and control of soft and continuum robot structures. Today, he presents modeling and control of new continuum structures. Caleb, are you there? Oh, yeah, you're there.
I'm here, yes. Thank you, Hattie. Thank you for the kind introduction. No, I'm good. You can go ahead and start it.
Very good.
Greetings, everyone. My name is Caleb Rucker. I'm an associate professor at the University of Tennessee. I'd like to start off by thanking the organizers of this workshop for all their hard work. They've been doing a great job, and I'm grateful to be a part of it. I'm going to talk today about some modeling and control for new continuum robot structures. So we're the REACH Robotics Laboratory at the University of Tennessee. Our work focuses on surgical robots as well as continuum robots, some soft robotics. We're concerned with questions of modeling and design and control. These are some of the students that I've worked with and that have contributed to the work that I'm presenting today. So in this presentation, I'm going to talk about a new bending actuator that we're working on in the lab. I'm going to give some thoughts on the constant curvature transformation. I'll talk about model-based estimation of force distributions and real-time dynamic simulation of continuum and soft robot PDEs. So this is work that my student Jake Childs presented at ICRA and RA Letters this year. The actuation principle here is not new at all. It's the same as a concentric tube robot. We have an outer precurved tube and an inner precurved tube, and when you combine them concentrically, they form a shape at equilibrium. And that shape is controllable by rotating the bases of each tube with respect to each other. The new thing here is that the precurved tubes themselves are not uniform tubes. They're bellows. So they have a convolution geometry that repeats down the tube, and we'll talk about that in a couple of slides. The main reason we did this was because we recognized that a bellows tube inherently has a very high torsional rigidity relative to its bending rigidity. So as many of you know, a key parameter that limits concentric tube robot performance is the ratio of bending rigidity to torsional rigidity. Now, a normal nitinol tube has a ratio of about 1.3, and there are many ways that people have explored in the literature to reduce this ratio by using laser micromachining to selectively remove wall material. And those methods can get the ratio down to about 0.4 or 5, but both rigidities are reduced in the process. So with a bellows tube, we can easily get that EI over GJ down to around 0.05. And that really changes the game, because at this ratio, there's no noticeable torsion at all during the actuation, even over large angular ranges like 135 degrees of bending. So the plot on the right shows the input and output angles, the base and the tip angles for a full range of motion, and they match exactly over that range of motion. And this actually makes it so that the torsionally rigid constant curvature models become accurate again. And it enables, for the first time, concentric tube robots to be built at larger scales for soft robot applications other than minimally invasive surgery. So this video shows Jake manually actuating a bellows tube pair, just showing how easy it is to rotate these tubes against one another and achieve these large bending ranges. There is some friction that needs to be overcome at the base when you rotate these tubes, but that friction does not propagate down the tubes into torsional deformation because of the high stiffness of the transmission. There are several ways you can make a pair of concentric precurved bellows. In the paper, we demonstrated 3D printing the entire actuator in one job in the assembled state. So both the inner and outer bellows are anchored to the build plate, and they're printed together. And then there's a subsequent annealing step where you can set the curvature of the entire device. Alternatively, you can design the bellows after a helical pattern, and this allows you to 3D print each tube individually and then subsequently heat set them and then subsequently assemble them by threading one into the other. These videos demonstrate the load-bearing capacity of the precurved concentric bellows. On the left, we're lifting a 100-gram load compared to the unloaded state. That's about 4 times the body weight of the robot itself. And on the right, we're picking up a UT-themed tennis ball, just to show how these actuators could be assembled into a gripper. So we put together a quick and simple constant curvature mechanics model for this robot. It's based on moment balance drawn at a section of the tubes. And it's basically the same thing as the original torsionally rigid concentric tube robot models, except for we have to account for different bending rigidities in the X and Y direction. So this model gives us the X and Y components of the curvature vector. And we can take the matrix exponential of the resulting twist matrix to obtain the transformation, which contains the position and orientation along the constant curvature arc. And this result is given by Rodriguez formula and then simplified to the equations shown here. This is a constant curvature transformation, but it's not the widely used one. It's usually written in terms of the conventional arc parameters, which are the curvature magnitude and the angle of the bending plane. But this alternative parameterization in terms of the Cartesian curvature components actually eliminates the well-known Jacobian singularity of constant curvature kinematics. So I'd like to take this opportunity just to say we should really be using Cartesian curvature components as the arc parameter space all the time, instead of the polar coordinates which most everyone uses. The singularity really is artificial. It's just due to the polar representation and can be removed with the right parameter space. Once you do that, you still have to evaluate functions like sine of x over x, but these are actually smooth and well behaved in the limit approaching 0, and the resulting Jacobian is non-singular. So if you're interested in exploring these claims in a bit more detail, 2 more independent groups wrote some very nice papers about it this year. Tom Allen recently at Robosoft and Cosmo Della Santina in RA Letters. And we're all using different notation and ways of deriving this transformation, but the forms are equivalent. Tom's transformation had appeared in another paper in 2017, and Ian Walker's group included it in a 2018 review. After we discussed this at Robosoft, I really searched my memory and scoured the literature, and it turns out that the same transformation appears in some of the very first concentric tube robot papers back in 2006 by Sears and Dupont. So hats off to Pierre here. I should also say that this Cartesian constant curvature transformation would exist as a special case inside some of the discrete Coursera approaches. I'm thinking about the piecewise constant strain work of Federico Renda and Frederick Boyer. So if you're interested in the generalization of this to that type of model, you can look up their work. So just to wrap up the bellows topic, a quick note about other manufacturing methods. We showed these can easily be 3D printed with FDM at a medium scale. Stereolithography also enables production at the centimeter scale, and electroforming can produce high-quality metal bellows at even smaller scales. And vacuum forming and roll forming may also be possible. So I'll move on to the topic of model-based estimation and control. For a rigid robot, we're all familiar with the forward kinematic mapping that computes end effector pose as a function of joint displacements, and the linear static relationship between end effector wrench and actuator force using the Jacobian. But for a continuum or soft robot, the above model doesn't hold anymore. Instead of an independent algebraic function that relates pose to actuation, we have a set of nonlinear differential equations with some boundary conditions, and the end effector pose is actually a function of both the actuator displacement and the end effector wrench. Further, the actuator force is now a nonlinear function of the wrench instead of the linear mapping given by the Jacobian. And these complications are all due to the fact that the robot body has the capability to store and release elastic energy in response to loading. But once we have the underlying set of differential equations and a method for solving them subject to boundary conditions, it's relatively easy to change what the boundary conditions are, change what they're specifying, and solve for a different set of unknowns. In this table from our 2018 TRO paper on parallel continuum robots, we list 6 possible model formulations that solve different types of control and simulation and sensing problems. So there are 2 versions of what we would call forward kinetostatics, where some actuation variable is specified, either force or displacement, along with an external end effector wrench, and then the end effector pose is obtained as an output. If the end pose and end wrench are known, we call this inverse kinetostatics, and we can solve for the required actuation variables that result in those end variables. The formulations that have the end wrench as an output we call wrench sensing algorithms, and these can be based on either pose combined with an actuation variable or the 2 actuation variables themselves, which we call actuation-based wrench and pose sensing. So there's different ways you could categorize these models and different labels you could give them, but I believe this chart and these terms are actually really applicable to all continuum and soft robots, and we found it as a useful reference and vocabulary for our work going forward. We can take all this modeling further and talk not just about the end effector wrench, but about force distributions along the entire body of the robot. And this is the current project of my student Vince, which he presented at ICRA 2019, so I'd like to highlight his work here. The idea is to take the shape of the robot itself, which can be estimated using vision-based techniques or fiber optic strain sensing, and then solve the inverse problem of what forces most likely produced this shape, subject to the form and constraints of the robot's kinetostatic model. Now I said most likely, and you may be wondering, is there only one unique loading for a given deformation? And from a theoretical mechanics perspective, the answer is yes. But from a practical perspective, the answer is no. When the reality of measurement noise is considered, there are many different force distributions that can fit the shape data within acceptable error margins. And we don't want to overfit the data and follow the noise. So what do? Can we get any useful information about the forces from the shape data? We take the approach of a constrained optimization problem, where we try to minimize the RMS error between the model prediction and the data over a space of coefficients that parameterize the force distribution. The constraints are that the underlying robot differential equations and boundary conditions must still be satisfied. So we've explored a smooth parameterization of force using Fourier series, as well as more discontinuous distributions using sliding Dirac delta functions, or point loads, that represent a set of discrete contacts along the length. And more recently, we've also explored a sliding Gaussian function parameterization. So the model and the approach are general and in 3D, but we wanted to first validate in some simple scenarios on passive elastic rods using planar data from a single camera. So the pegs in the pegboard here in the picture exert forces that are normal to the rod surface. And we have a base force and torque sensor that we use for validation, but the algorithm only uses the camera data for estimation. And the results show that the estimation does indeed give useful information. Even if the load distribution is not fully determined by the data within the measurement noise, we can still identify regions of high force and rough magnitudes of the forces involved in those regions. We particularly like our parameterization in terms of sliding point forces because it gives us what could be considered a conservative worst-case scenario where the loading is highly concentrated at a single point or a few points. And we can adaptively change the number of point forces in the model and select the result with the fewest number of point forces that still fits the shape data within a reasonable tolerance. And this worst-case estimate could be useful for medical applications in which rupture force is a concern. So we can run this method in real time at the camera rate of 30 frames per second. This video is the algorithm running in real time, and it's taking a single Levenberg-Marquardt step every frame. And that allows us to see the progress of the estimation algorithm in action. And it keeps up pretty well with the changes, though we haven't evaluated the bandwidth formally or tried to optimize it by tuning the parameters of the optimization routine. And this particular video is also using a different force parameterization based on Gaussian functions that I mentioned earlier. And finally, we did a couple of one-off experiments with even more loads, and then a 3D case including torsion and gravity. In the 3D case, the method still gives useful information, but the error is a little bit larger. And we believe that incorporating more data, such as base force measurement or a tip pose measurement, can improve the robustness in 3D. And briefly here at the end, I'd like to highlight our dynamic simulation work for soft and continuum robots. This is my student John's work in IJRR and a previous IROS paper. We applied an approach to solving the dynamic Kosarat partial differential equations, PDEs, directly by using an implicit time discretization that is inherently stable and thus enables large time steps to be taken. And this procedure creates an ODE in the arc length variable, and solving that ODE at every time step is very analogous to solving the static models that we talked about earlier, and can be done with the exactly the same methods. So here's the paper and some of the examples that we included in it. We have a tendon robot model, a multi-rod parallel robot model, and a fluidic actuation model here. If you're interested in this, we included some sample code in the paper, and we also set up a GitHub repository for the methods that includes several example robot models. And hot off the presses, we have implemented this same method to simulate the dynamics of concentric tube robot snap-through instabilities. We derived the PDEs for the coupled tube system, and the method for solving the ODE here is a little bit different because we needed to take very small time steps in order to resolve the quick motion during the snap. So it's more of a finite difference approach for the ODE and arc length. But we can now predict not just whether a snap will occur, but what will happen during the transition. How fast will the tip move? How much will it overshoot? When will the oscillations die out? So it's a tool that can be used to design the snap behavior itself or to make sure that it is relatively benign. So thanks for your attention. I'm going to end this presentation with time to spare so we can have more time for questions. And I'd like to finally acknowledge again the support of my university and of NSF, who has funded all of this work through several grants over the last few years.
Very interesting talk, Caleb. Now it's time to answer a few questions.
So if I may start. Yeah, thank you very much for the presentations. As always, very cool works. Among the various things that I would like to ask you, I will focus on the work about force sensing. It's with distributed force sensing. It's very nice, and I have two questions. First of all, is do you think that dynamics has dynamics should be considered, or more in general, is there anything to gain by considering also dynamics instead of only quasi-statics? And the other one is you are considering now to know the complete shape of the system, which is something that it's amazing that you could get experimentally, but still you have to use an external camera. And so I wonder if you are thinking about some extension in which you have only a finite number of measurements on the along the robot.
Yeah, good question. So if I remember back, the first question was about quasi-static versus dynamic models in force sensing. And our initial desire was just to tackle the quasi-static problem, because that seems very relevant to various medical procedures. And especially at the small scale, a lot of these robots, their dynamics are so fast that it's not feasible to really consider real-time dynamic force estimation. But I do think it's a good direction for our future work. In a larger setting with soft robots that move a little more slowly, and those, you would have to formulate the dynamic model with forces involved in it, external forces involved in it, as well as the inertial forces and dynamics. So we haven't tried to tackle that problem yet, but I do think it's a relevant problem, especially in the larger soft robotic domain. It all depends on the time scales involved and whether or not the dynamics are significant over those time scales. And if they are, then you would have to adapt this approach to work with a dynamic model instead of a quasi-static model. And I think the result would look something like a dynamic observer that's got force states in it that you're trying to identify from data. So the second question about what data do you need to do this? So that's actually what we're kind of exploring right now. Our current work is to extend this paper to robot, more directly applicable force sensing on robots that are actuated, not just passive rods. And so for that, you may not always be able to see all of the backbone structure or with good clarity and get that nice continuous set of points. So we are investigating, can you do this with sparse data, with just localized point measurements? And the answer is actually yes. And actually it somewhat improves the estimation, because we found that initially the more points that we used, it sometimes, if we got too many data points, sometimes the estimation was worse, because we're essentially trying to fit noise, right? But if you have kind of so we purposefully downsampled the camera data to, I think, maybe like 50 to 100 discrete locations on the rod, which was much sparser than the pixel data was. so we did that before even applying our algorithm. And so I don't think the general approach will have a problem with sparser data. You just may have a coarser representation of the actual force distribution, which is okay because we're basically just trying to, these force distribution estimations they're estimations. They're not exact values of force, but they're indicators of where forces are applied and roughly how large those forces are. So I think the sparse data problem is not going to hinder the applicability of this work. And that there's other types of data that you could include into this framework. For instance, we're only looking at the positions along, but if you had measurements of pose or position and orientation, or if you had measurements of force, that you can include as constraints in the estimation problem, that's something we can do as well. So we're currently kind of looking through all those combinations and trying to identify what problems can we solve well with what kinds of data. And that's the current direction of our work on that. Good questions. Thanks.
Thank you.
Great. We have a pretty long question in the chat. It says, thank you for the interesting talk. I have a follow-up question about this question of a small time scale dynamics modeling. When talking to other researchers about soft robotics work, I often get the feedback that if we wanted to do high frequency control, we should just use rigid robots, and that taking advantage of soft system means having large delta T control and allowing the system to conform to its environment. In your work, have you seen a compelling justification for high frequency, high performance soft robot control?
Yeah, so I think I would tackle it in the context of what application are we looking at here. If you're talking about a large robot in an industrial setting having to move extremely fast with high precision, then a rigid robot approach is the way to go there. If you're at the very small scale inside the body, then it may not be an option to have a rigid robot architecture in there. And so that's kind of that's the reason that we were looking at those small timescale dynamics for concentric tube robots, because those are the only robots that can really be built at that scale, and they're sort of inherently flexible because they're so small. And so but then they have this interesting fast dynamic that can be dangerous of snap through. That's been recognized for a long time, and so the question was, well, how can we know this happens? Can we describe it better? Can we model it and figure out what's happening during those very small timescale transitions, possibly to avoid them or make sure that they're not going to be too dangerous, and also possibly to use them. It's true that if you insert a needle with high velocity, sometimes there's less tissue damage than if you insert it with slow velocity. So for procedures involving needle puncture, that could be an interesting thing to look at. So I'd have to think of your question a little harder about, have I seen a compelling justification in general, soft robots for high frequency, high performance soft robot control? I guess I would say, it depends on the application requirements. Yeah. As long as your control bandwidth is high enough for what you want to do, I think it's fine. If you're talking about like extremely high performance stuff, like, really fast running robots or something like that. Bandwidth is one of the drawbacks. Low bandwidth is one of the drawbacks of soft robotics in general. But it's not to say that it's not a desirable feature. I think it's good for us to try to figure out ways to make soft robots that are stiffer and have higher control bandwidths, while still maintaining a degree of softness. So it's a good open question for the field. Thanks for bringing it up.
great. You have a comment from George. Maybe you can replicate data
Sure,
at the same location to filter out the noise. I think that comment needs further talk between you two.
Sure.
Just a last question, if you can quick answer. The in vivo application is a great example. Thank you. Okay, that wasn't a quick question.
Sure.
I have actually a quick question myself. We have still 1 minute. So you tried using base and tip load reading for estimating the load. How that work? How did that work?
So we weren't actually using the base sensing as part of our algorithm. We were just using it for validation. So just to check and see if the forces that our algorithm was outputting were actually consistent with the magnitude of forces that we were seeing at the base. So we're currently also looking at, well, what if you did use that data? If you had shape data plus base force sensing data, can you get more accurate results? And so we're in the middle of figuring that out right now. Yeah.
Great talk, great discussion. Thank you, Caleb. Now we move to the next talk by Tanya Morimoto. Tanya is here. I'm gonna briefly introduce her. Tanya is an assistant professor in the Department of Mechanical and Aerospace Engineering and in the Department of Surgery at the University of California, San Diego. Her research lab focuses on the design and control of flexible continuum robots for increased dexterity and accessibility in uncertain environment, particularly for minimally invasive surgical interventions. They are also working to address the challenges of designing human in the loop interface for controlling these flexible and soft robots, including the integration of haptic feedback to improve surgical outcomes. She's going to present localization and control of growing robots in medical applications. Tanya, do you have anything to add before I play your video?
No, that's it. Thanks for the introduction.
Okay, great. Now it's
Hi, my name is Tanya Morimoto, and I am an assistant professor at the University of California, San Diego in the Department of Mechanical and Aerospace Engineering, as well as in the Department of Surgery. And I'm very excited to have been invited to talk at this workshop, even if it is virtual. And I'm happy to be talking a little bit about some of the work we're doing in our lab on localization and control of growing robots, particularly in medical applications. So growing robots are an emerging type of soft robot. You can see a video of one up here on the screen. They generally consist of a thin-walled hollow membrane that is made into this sort of hollow tube, as you can see here. And the material at the tip of the tube is inverted or sort of folded back into itself. And then as we pressurize the base with fluid, this material can extend or sort of evert from the tip, causing the sort of growing motion that you see here. And these growing robots can actually extend to be many, many times their original length. And because of a phenomena that I'm going to show here, they actually can apply very little shear forces on the environment. So as you notice in these still frame images, we have these sort of markings in red and green on the outside of the robot. And even as the tip of this robot is moving forward, the body of the robot, as you can see by the markings, is remaining stationary with respect to the environment. And because of this, it can apply very little shear forces on the environment, which can be good for applications where you maybe need to be a little bit more careful. In addition, these have natural compliance that allows them to easily conform to highly curved paths that would typically be very challenging for traditional sort of rigid robots to navigate. And another reason why I'm very excited about them is for their potential to enhance robotic surgery. And this is because these types of growing robots could be very useful in highly constrained regions, particularly inside the human body, that can be difficult to usually access in a minimally invasive manner. So in addition to these types of growing robots that you see here that are just sort of growing in a straight line or would conform to whatever environment it might be growing through, we also have two other sort of manifestations of these growing robots. And so the first we can see on the left here is that these can actually be fabricated to have a pre-curved shape to them. And so the idea here is that as the material is everting from the tip, it actually grows out into this predetermined curved shape. And so here we're just doing a single sort of tight curvature, if the video will continue playing, but we can do these with multiple different curvatures or shapes as well. In addition, as we can see, there we can see the pre-curved shape. Sorry for the lag on my computer. In addition, we can fabricate ones that actually have soft actuators that enable bending of our robot in this sort of constant curvature. And so what we do is we have these soft actuators that are arranged radially around our body of our fine robot itself. And what happens is as we inflate each of these actuators with air, they actually contract, and that is acting like a tendon force, which is allowing us to control the bending of these robots as well. So despite the significant potential for these robots, there do remain a number of challenges for practical implementation, particularly in medical applications. And so the first that we've been interested in is this idea of state estimation. How can we actually localize points along the backbone and reconstruct and understand what the shape of our robot is in any given point in time? And this is particularly important in medical applications where you want to make sure that you have a really good understanding of exactly what your robot looks like at any given time. And even a little bit more, taking a step back from that, a little bit simpler even, is just where's the tip position in space? How do we know exactly where the robot tip is as we're growing, as we're interacting with the environment? And so this is another challenge that we believe is important to tackle before we can really implement these robots. And so if we are trying to solve this localization problem, the next question is, how do we actually incorporate sensors, whether it's for localization or for some other estimate of the state of the robot? How do we actually incorporate these into a soft growing robot? And so this becomes quite a bit of a challenge. We have this soft kind of fabric or plastic material, and we're also everting in this growing motion. It becomes pretty difficult to figure out how can we incorporate these sensing elements. So one of the things that we have been trying to tackle first is this idea of tip localization. And this is also can be challenging, particularly with these robots, because we need to make sure that if we are looking at medical applications, we want to make sure that we can actually work through, our sensing works through the human body for localizing the tip, and also that it doesn't require any sort of line of sight. And so the approach that we have come up with, that I'm going to be talking about today, is to actually use a permanent magnet. So we can see we have this ring magnet here. And in this video, you can see sort of how we first invert the robot, as I was explaining. We invert or fold it in on itself. We then take this magnet that we're going to use for sensing, we put it over that inner portion of the material, and we push this magnet all the way up to the tip of the robot. And then what's pretty neat is that as we inflate this robot with air here and we pressurize it, we can actually see that the magnet stays at the tip of the robot throughout this growth process because of the friction between the magnet and the inner material, and because of this force that's being applied by the pressure inside of the robot. And so now that we can see that we have this way of keeping the magnet at the tip of the robot, now in order to track the robot tip, it's now turned into a question of how do we just simply track the position and orientation of this magnet. And so we decided to investigate 3 different approaches to tip localization. So people have done, tracking of these magnets before, and so one approach is to do a model-based approach where we model this magnet as a dipole. We also looked at a completely data-driven approach, sort of a black box. Let's just learn the position and orientation of the magnet purely from sensor data. And then finally, the one that I'll talk the most about is this sort of hybrid approach between the two. So just to start with this first approach, we have an array of sensors. Magneto-inductive sensors is what we used here, but really you can use any sensor that can sense this magnetic field strength or flux density. And so we can approximate our permanent magnet as a dipole, and then we can calculate the magnetic flux density at the location of each of the sensors in our array. We use four sensors here. And then we can do an online optimization over the magnet pose in order to get our position and orientation. Now, this method works relatively well in most scenarios. However, when the magnet is very close to the sensor, it does become inaccurate. In addition, there are sort of these unmodeled nonlinear behaviors that our sensor can exhibit, including hysteresis and saturation. And we do need to know exactly where our sensors are beforehand in order for this method to work. So there are a few limitations to this approach. And so the second approach that we looked at was a purely data-driven approach where we used neural networks to really try to capture some of these unmodeled effects. And so we use this long short-term memory network because that it is shown to be adept at predicting on this sort of sequence data, which is important to us since we want to try to look at solving some of the issues that do depend on time. And so we took this sort of completely black box approach. But a few of the limitations are that you really do lose any sort of physical significance that we had with the physics-based model. It's also completely tied to whatever sensor configuration that we have. And so the kind of hybrid approach that we've come up with and that actually performed the best is that we start with knowledge of our sensor location and some guess of our initial magnet pose. And then from there, we actually train an LSTM network to learn simply the residual between the output of our dipole model and the individual sensor reading. And then from that, we can actually just correct our sensor values at each time step and use these corrected values instead in an online optimization to find the magnetic pose, just as we did in the first approach. And then we can use the output of this optimization to initialize the optimization at the next time step. And so a benefit of this approach is that it really leverages additional data to try to capture some of the phenomena that were hard to model. And it is also data efficient compared to learning the entire model from scratch. We're not just throwing out this physics-based model that works pretty well most of the time. And we did find that this was more accurate than either of the other two approaches. So the way that our setup looks is we have a test platform that we grow our robot with the magnet tip on top of. We have a series of these magnetic sensors underneath, they're magnetoinductive sensors. And we use an overhead camera in order to capture our reference pose measurements. And so we use the camera and we have a cap that's shown here that has some fiducial markers to make it easier to track. And that's how we get a reference pose. And this is also what we use to generate training data for our neural network. And so this is an overhead image of the test setup as well. You can see 4 of the sensors in red, as well as this cap with the markers on it that we use to capture the reference pose. So here is a few videos of the tracking in action. So we actually then grew our robot through 2 different constrained environments. You can see here, we have this sort of S-shaped curve as well as this spiral. And we can see that being plotted, we have in blue the actual tip position as measured by our overhead camera system. And we have in red our measured tip position as measured by our permanent magnet-based localization. And so what we can see from watching this is that even as our robot is interacting with the environment, this localization method still gives us this accurate estimate of the tip position of our robot. And we can see that in this planar case with the two environments that I just showed, our average error for the tip position was around 3 millimeters, and our average orientation error was about 6.5 degrees. And so we can see that this demonstrates the ability of this approach to effectively track the tip of our growing robot. And so we also wanted to demonstrate the localization method works well even in the 5-DOF case. And so what we did here, we altered our test setup a little bit. We deployed the robot in the spiral environment, and we actually changed the inclined angle of the sensor bed from 0 degrees all the way up to 30 degrees in this 10-degree increment. And we estimated the position, now 3 different values of the position, as well as 2 orientation values. And what we can see is that we were effectively able to localize in 5 degrees of freedom as well. We do see that the orientation error is consistent with that of the planar case. And we see that the position error is slightly higher than we saw in the planar case, probably due to estimating this additional spatial component of the tip position and the errors that come from that. So now that we have demonstrated this ability to localize the tip of our growing robot, we want to start to try to figure out how can we actually use this to control where our robot is going and how can we follow some type of trajectory. And so what we've realized is that a lot of these analytical model-based control approaches for these growing robots can be very challenging to use with existing control techniques. And so in addition, a lot of these models are unable to capture some of the important phenomena of these robots, such as friction and hysteresis. And so instead, what we've chosen to do here is to estimate the Jacobian directly from the data. And we are making online updates to this model of the Jacobian as our robot is navigating its workspace. And so this simpler model that we have can then be used with existing control techniques to compute the actions that our robot needs to take in order to achieve some particular task, move along some particular trajectory. So here is a brief overview of what our control loop looks like right now. We basically start by having some initial estimate of our Jacobian that we get by moving our robot in all different directions. We can then use this along with our predefined target trajectory to compute what actuator control signal values we need to actually get our robot to move the tip position that given amount. And then from there, we send this signal to our growing robot and it moves, and we can measure using our localization method that I just described, the position of our tip of our robot. And then we can use this information to both update our control block here, as well as update our estimate of our Jacobian. And so this is work that we're currently just working on in the lab right now. So we are in the process of hoping to test it on hardware within the next few days. But right now I have a few simulations at least to show of trying to have the tip of our growing robot follow this sort of spiral-like path. And we can see that we have these estimates on what the actuator effort should be, how much pressure we need in each of these 3 actuators oriented around our robot as we're trying to follow this particular trajectory. And we can also see the error of our tip position, at least in this simulation. And so our next step is actually to hook up all of the hardware that you see in this photo here. And we have 2 cameras, again, so that we can get our actual tip position in space as well. And the next step is really to test all of this put together on the hardware in both unconstrained as well as constrained environments. And with that, I would like to conclude and thank you for listening. I hope to be able to speak with some of you in the future about some of the work that we're doing. Thank you very much.
Thank you, Tanya. Very impressive work. Very different in terms of what we've seen and in the workshop today, in terms of hardware and challenges in modeling. Now it's time for answering some questions. We have one from Thomas George. Thomas, maybe you can ask it yourself.
Yeah, again, thanks for the talk, Tanya. So my question was like, how would you specify your target trajectory if you don't know how the environment looks like?
Beforehand? Yeah, no, that's a good question. I think there's a few different models that we see that could sort of work for this. So one is maybe you do some sort of preoperative imaging and have some idea at least of where you might want to be going. Another idea that we have is that maybe you use this sort of in conjunction with some sort of imaging modality. So for example, maybe you use X-ray imaging, get what we call this sort of roadmap, and then you just, instead of using constant radiation throughout the procedure, you could use this to sort of update your estimate on, on your roadmap for where you're going, and then turn on the X-ray imaging to sort of check at critical points. So yes, I agree. You might not always know exactly where you're going at any given time.
Is it possible to map your environment just by looking at the tip position?
I guess it depends on how accurate of a map that you would want. Yeah, I think doing something more like putting a camera at the tip and doing a slam or something is probably a better way to map your environment.
Yeah, thanks.
Yeah, thanks for the question.
Hey, hi, thank you, Tanya. There is time for one more question, Hadi? Yes, thank you. Hi, Tanya. Very interesting talk. I was wondering, I was trying to relate your system, the eversion system, with the other system we have seen so far, and for instance, the very impressive FEM simulation people have proposed for, let's say, more traditional soft robots, if you can say that. And I was realizing that there is a substantial difference between your system and traditional soft robots again, because the actual, if I would like to model your system, the actual domain of your beam, let's say it is a beam, it's changing over time. It's not elongating the beam itself. It's a real changing of the domain of your system. It's a growth, in fact, as you call it. So did you or anyone in your team try to think about how this could be possible approach? Do you have any attempt? Do you know any attempt in this direction?
On sort of the modeling side,
yeah, sort of modeling of this growing effect, which is different from the deformation that we are used to now in soft robotics.
Yeah, no, I think that's definitely an interesting direction. And I think, a lot of different groups related to where I was for my PhD. So, Alison Okamura's lab and Elliot Hawk's lab, I think many groups are working on similar things. And I think maybe some of them are working more on the modeling side, as you're saying. We haven't started to investigate that yet, but I think it is an interesting direction to go. Yeah.
Thank you.
Thank you. We have a question from Fook. How many actuators do you use to control the direction of the robot?
We use 3 actuators, similar to kind of having the tendons oriented around the robot.
And Godaba asked, thanks for presenting this interesting developments on the eversion robots. Can the magnets be placed closer to the base of the robot? I mean the magnetic flux sensors.
So can this, I'm a little confused. Can the sensors be placed closer?
Yeah,
so,
hi, just to clarify, for example, you have the flux sensors under a platform, but for example, in some environments, we might want them closer to the control system from the point the robot is being deployed.
Oh, I see. Yeah, so really you would want them as close as closer towards the magnet itself. If it gets too far away, then we won't have a high enough signal strength to be able to track it well.
Yeah.
So we are looking at how can we sort of optimize the placement of the sensors as well in order to get the best tracking ability.
Okay, thank you.
The next question is from Caleb. Caleb, do you want to ask it yourself, or I just read it out?
Sure, I can. I was just wondering about the Jacobian update. Yeah, it was a great talk. So you're using that. I forgot the equation, but it's a minimization of the change in the Jacobian subject to the new sensor information. And I was wondering how often does that happen? Maybe you mentioned that, but I might have missed it. And are you doing any other like data filtering? And is it possible for like the inertial dynamics to, mess up that Jacobian estimation? Because there's the robot could move, in a way that that the actuators did not directly cause.
Right. Right.
Yeah.
No, I think those are all good questions. So it is ongoing what we're working on currently, but the way we're currently doing it is we do low pass filter the data as it comes in, and also the robot moves pretty slowly in its current form. So I don't think we're too worried about it moving in a way that is going to mess up the estimate. I think that
cool, yeah.
The rate that it
so
moves.
it's basically kind of a quasi-static
Mm-hmm.
approach. Okay, yeah, that good. Thanks.
Yeah. No, thank you. And thanks for your talk as well. It was great. My whole lab listened to the recording a few weeks ago. So I see Nabil.
Great. The next question is from Mr. FDO. He asks if the magnets causes any interference. I assume in medical applications like MRIs.
I see. No, I don't think we're too concerned about that right now, at least. Yeah.
Okay. And we have a question from Nabil. There are ways where you could compute the local derivative of an offline computed magnetic field and use that information in a resolved rate approach to update your estimates of the new location. Have you compared your approach to those?
Thanks for the question, Nabil. No, that's a great question. And I think that's a good point to bring up. We have not compared that to our approach, but I think that's definitely something that we should do. Yeah, thank you.
Could I ask a question?
Yes, of
Sure,
course.
go ahead.
Hi, Pierre.
Hi, Tanya. I enjoyed your talk. Thank you for that. Inevitably, someone is going to ask you to compare your system to the existing electromagnetic sensor systems that are out there. And there's some points of comparison in the sense that the ones used clinically have the, effectively the transmitter in a pad under the patient. So it addresses exactly that earlier question about, can you put the sensors near the base? No, you're going to put it under the patient. But an alternative approach to what you did that might be interesting to consider, these sensors and the leads, the electrical leads are so small, you could consider putting an array of these that extend, out the bag and then in the eversion, right? So that as the thing everts, another sensor is popped out so many centimeters from the previous one. And you could get the whole shape as well as how much is everted. So it might be a nice point of comparison to what you're doing now.
Yeah, no, I think that's definitely a good point. I think the main challenge is making sure that the robot can still grow. If you're adding all of these sensors inside, I am a bit worried about the friction and the ability to evert, because especially at the tip, the fabric is completely folded over on itself. And so I think that eversion is going to be pretty tricky, but yeah, I think it's something to explore, definitely.
The electrical leads on these sensors are just so small. And if you embedded them in the bag itself, I see. Change the properties very much. So that, the bag, it's just the bag that's still sliding and everting, but the sensors are embedded in the bag the whole way, out and back in.
Yep. Okay, no, that's definitely a great point. I'll have to look into, getting some of those. Thank you.
Thank you. We have time for a small question before we move to our panel discussion chaired by Cecilia. Okay, we have one from Andrew. Related to the eversion question, have there been approaches considered to retract the device?
Yeah, that
yes, ongoing work, and definitely a good question. So I think there's a few current approaches. One is to sort of deflate the robot a bit and then pull back on the base, which is not necessarily ideal because you're sort of getting these interactions that you were trying to avoid in the first place. There's some mechatronic devices that have been developed that go and remain at the tip and basically try to pull the material from the tip back inwards on itself. But sort of scaling those down to a size that would be useful in a medical setting is challenging. So I think the answer is, people are considering it, as are we, but I don't think there is a great solution yet.
Okay, great. That final question, we finished the keynote talks and all of the presentation. And Cecilia, it's yours for the panel discussion.
Thank you. I'm very happy to chair this final session of this exciting event. And please let me first thank all the invited speakers, because I think they gave such an exciting picture of the latest achievements in this field. And we have seen that it's actually a lively field with a lot of research, a lot of new ideas and new achievements. And thanks also to the poster presenters, of course, because they added a very valuable new concepts and new ideas, very stimulated as well. Actually, it's their time now, because it's time to give the well-deserved awards to the posters and their authors. But before that, please let me make another acknowledgement to the other workshop organizers, so Thomas, Federico, Cosimo, and Hadi, because they did most of the work. Actually, they did all the work, and I think they did a very good job in putting together such a valuable event. And also for proposing this live session, because I think that it added a lot, especially in these times where we feel isolated and we have to be isolated. So thank for all this. And also thank for organizing the awards, which means, finding the sponsors for that, and also serving in a sort of small board that made the selection of the winners. So my little applause to all these people, and of course, thanks to the attendees for being still here after a quite long day, which is not finished. So let's go into I'm sharing a few slides to go into this small, simple ceremony for the best posters awards. I hope you can see my slides. As I mentioned, there are sponsors behind them, and they are Frontiers and Disney Research that we, of course, to which we are very thankful. Okay, so let me start with the finalists for these awards, and they are the posters titled Kinematics and Shape Sensing of a Collaborative Continuum Robot by Andrew Orekov, Jeongwoo Seo, and Nabil Simaan. Then Control and Trajectory Optimization for Soft Aerial Manipulation by Joshua Fishman, Samuel Ubelaker, Nathan Hughes, and Luca Carlone. And then Introducing Florio, a modular integrated development platform for soft robotics by Ali Starmanov and Joseph Paradiso. I think we should congratulate with them already, because it's already, a big achievement to be in this small number of 3. But we have an additional order for them. So starting from the 3rd place,
A big applause to Joshua Fishman, Samuel Ubelaker, Nathan Hughes, and Luca Carlone for control and trajectory optimization of software manipulation. I'm sorry we cannot hear a big applause through Zoom. Then second place, we have Andrew Orekov, Jeongwoo Seo, and Nabil Simaan with kinematics and shape sensing of a collaborative continuum robot. Congratulations to all of them. And then, a small drum roll, the first place, and of course, we know already, it's Alish Darbanov and Joseph Paradiso with Introducing Flowio, a modular integrated development platform for soft robotics. So another big applause by all the attendees, I hope. So, and then Thomas, I think I will take care of the practical issues related to that. So we now have some time for continuing the lively discussion that arose during the presentations. Actually, there are several points that were touched and were discussed. I'll try to check the chat window to see your comments and possible questions to the lecturers and presenters. So I would like to start by raising some of the points that we have listened and that we have discussed a little bit. Let me start from maybe from the end, because a part of this point was also raised during the latest presentation by Tanya. And it was also mentioned by in Walker's presentation. So of course, this workshop was focused on modeling and control of soft continuum robots, and we always think of controlling the end effector, but we have seen that it is also important to control actually let's say the posture, the curvature, especially for this kind of robots. And actually, we have touched a bit the idea of controlling even more, not just the curvature and the end effector position, but the overall robot, let's say, configuration. What I mean is, in most of the presentations yesterday and today, we have seen that soft robotics is, I mean, not just using soft materials for building robots, but going beyond the traditional robot idea. Many presentations started with the industrial robot. This is the industrial robot. This is what we know, and we can control and model perfectly. But now we have soft robots. Why do we have them? Because we want them to do something that rigid robots cannot do. So why don't we start thinking of modeling and controlling them from what we expect they do? And the reason why we want robots to be soft is that they are highly deformable and can, for example, access tiny spaces. So what does it mean modeling and controlling them in this case? It's not, of course, just controlling the end effector position. It's controlling the curvature when they have some bending abilities only, and that's fine. But it is also very much related to interaction. We have seen some very, very interesting examples of how actually robots adapt to the spaces they have to access. And if I should take a look even forward, I mean, a perspective view, I expect that we need to model and control bodies that can really change shape. This is something almost possible with soft robotics. We have seen some examples of growing robots, but we can think of robots that can morph and change their shape depending on the application. For instance, we should think of robots made of materials that can self-heal, which means that they can be damaged and change their shape and change their motor capability. And then they recover, so they change again. So I think that all this, I mean, this scenario is putting forward a lot of very interesting new topics for modeling and control. So in summary, what I think is that a further step is moving from, let's say, the traditional approach to modeling and control adapted to soft robotics to maybe even different approach, starting from the functions that we want in our robots. Actually, this workshop was entitled application oriented, and that's one of the meaning of it. I don't know if I was clear enough, but I tried to depict a scenario view and hopefully stimulate some other comments from your side. So I see something appearing. What are the complementary technologies that need development to help solve soft robot control? And for sensing, for example, springs to mind. Very good point. Very good point. I have another one related to this that I was keeping for later, but that's interesting. So this is about complementary technologies. So if we want to have a body that adapts to the spaces that it navigates, and if we want to control the interaction, we probably need to improve the sensing capabilities.
Thank you, Cecilia. Let me, so while you were talking, had something I would like to share. One related comment might be of also relating to the application-oriented theme of this workshop. In your opinion, for the audience and for the speakers, how much we should focus on general theoretical result in control, and how much instead we can focus on tailored solution for specific application and specific design and specific machine. This I might be a bit naive in that, but in these 2 days I've been seeing, if you want, a little bit these two approach. Yes, this is a question I would like to pose to everyone. And yeah, what do you feeling you are doing? You are doing more theoretical result or practical control solution for specific design?
This is also a point that came out in some of the presentations, because someone said, okay, sometimes we like these soft robots that are more demo robots than the real applicable ones, but because they are very good platform for our research, they are challenging platforms for us for developing new models and new control techniques more on the theoretical side. So I think that's a very good point. Do you think we still miss the technologies for building the robots, or?
That's quite certain in my opinion. But at the same time, we can build several robots. I mean, of course, replying to my question, that of course we should do both and converging as usual. Again, maybe once more, I can notice that another big difference between soft robots and normal robots, that said it probably several times, is the lack of a uniform topology, if you want, a uniform, yes, theoretical topology to which one can refer to a bit more abstract, in an abstract form, let's say. There are some of those topologies have been condensed. I'm thinking about beam theory, for instance, in my case, which is a kind of reference, yes, topology of the model that one can use as abstract reference. But this is absolutely not enough. Maybe there are others of this condensed form. For sure, there are many, and maybe too many. I guess, I hope that moving forward, we will be able to yes, standardize a little bit our hardware, and at the same time, the topology of the model, and so that people can try to develop theoretical control, which can certainly find application, because if a theoretical control is designed around an abstract model that find many instantiation, then it becomes extremely useful in general. But at the same time, I see that, for instance, I'm thinking about the excellent work of Marc Killpack, where it looks to me that in that case, they were trying to make things that work for their using very advanced also modeling technique, and but try to adapting them not to soft robotics, adapting them to their platform, which is also a way to probably improve and a way to go forward.
I wasn't sure. Is this open for public commentary?
Sure.
Yeah. So you know, when I look at the works here, you know, certainly they're all very interesting works. But when I look at the field of soft robotics and the way it has historically evolved, there's been a necessary focus on fabrication techniques. We are now getting to the point where some of these fabrication techniques are becoming more and more widely accessible to us. When you look at the modeling, kinetostatic modeling generally is becoming more and more understood. Dynamic modeling still is a big challenge, but if you look at the you know, at the end of it, the goal is to produce designs that can actually work for a particular application. So I come back to the question of the trade-offs between model complexity and model simplicity and the ability to identify the model and then update it in real time. It seems to me that there's a lot that we could still learn from with regards to looking at the trade-off between these models and then focusing more on parameter identification, calibration of soft robots in a pragmatic way that can actually get you to a point of solving problems. That's one problem. The other problem is task-based design of soft robots with minimal actuation and sensing still remains a completely uncharted territory. You know, the entire area of structural optimization from civil engineering has been developed, but somehow we haven't really adopted it yet. There are some people that do some really nice work related to robots with flexures, but not at large scale for soft robots. So that still remains an area of opportunity for people to look at.
Anybody wants to comment? Actually, related to this comment and to the previous one, I'm wondering what other, how can I say, kind of expertise or disciplines do you think we are missing here? That was also mentioned in the very first presentation by Frédéric Boyer. Because he said the Reisner approach is not so much used because it's not so much known in the community. So do you think that we miss some other community to take these challenges? So may I ask, for instance, I mean, mathematicians, but may I ask who of you is not strictly a roboticist or control person? Nobody, maybe. Which is, I mean, what I wanted to show. So probably we should find a way to attract also other scientists from other disciplines.
If I may comment on that, I absolutely feel this pain a lot through all this year of learning. I mean, I always have been almost inhibited by the amount of work you have to learn, you have to understand from other community before feeling, okay, maybe I'm doing something which makes some sense. It really take a lot of time, and suddenly you notice paper from I don't know, the 95 somewhere in structural dynamics, and you say, wow, this was so significant for my work. So I think this is one of the opportunities of soft robotics, which it's really break the boundaries to building this new machine. And but I think other community are listening a little bit. For instance, my postdoc come from civil engineering, and I know, and they work a lot with metamaterial as well, which is, if you want, also related to soft robotics somehow. And yes, absolutely, this is very, very important, and I think it's happening. So it's like optimistic comment. I think it's happening, and it will happen more and more. From everyone, there should be probably we should be humble enough to receive and give sometimes, and maybe receive probably knowledge from those community. But at the same time, we can provide really new challenge and new problem to solve.
Yeah, and I think there are so many challenges, so interesting challenges, that we can definitely attract other communities to work with us. I have some comments in the chat, so let me look at them. So Ali asks to all the panelists, one of the most important aspects of soft and continuum robotics is human safety. It includes human-robot interaction, like in medical applications. So what are the challenges in the works of each of the panelists in this regard? And what problems need to be addressed in the coming months to make significant progress in this regard? So the challenges in physical interaction with humans, especially in the medical field where the interaction is very strict. I don't know, maybe Pierre can start.
Sure, I'll make a comment. And let me actually back up before answering that to address some of the comments Nabil made. I think that, you know, what he was observing is important. Every field goes through a, you know, a sequence of, or a maturation process. And so, you know, he mentioned how fabrication was the first problem. We know how to make a lot of these things now. And right now we're figuring out how to control them and how to model them. And ultimately, maybe the interest will turn to how to apply them in a real setting to a greater extent. And so that can happen to a field. It can also happen in one's career. I have to admit, you know, when I've been at the hospital for a decade now, and when looking at every problem I take on has to be clinically relevant. And I've reached the point where I realized that a lot of the modeling work I was doing lots of modeling work, but I realized the models were good enough for the problems I wanted to solve. The models and most of the control were good enough. And so I, you know, to a certain extent, I stopped trying to make more sophisticated models. I was just trying to figure out what was that, you know, secret sauce combination of things that I already had that would make the problem work. So it's interesting how things can evolve even in your own career like that. Now, with regard to, you know, to soft things, soft robots and continuum robots, you know, my challenge over the last, well, even backing up, you know, I tried to write the introduction to a paper a year ago or so, and I wanted to have this grand story introduction about, you know, how robots were so ubiquitous. And I think I talked to Nabil about that. I was trying to figure out how many robots are out there in the world, and I was very disappointed. You know, it seemed like there were, you know, under 10 million robots in use in the world. I'm like, oh my gosh, that's, you know, that's crazy. But my challenge over the last decade is to try to figure out where the heck does a robot really add value in medicine? And it's so tough to find one. And so I've sort of tumbled into looking at this space of catheter-based interventions. And it just happens to be a case where, you know, cardiologists already figured out that long, soft, flexible things work really well to address these issues of safety. You know, so the catheter is like a perfect test bed to walk into and then see where I can develop additional tools to make it more effective. But I can't claim that I'm really solving the safety problem because the mechanical design gets you most of the way there.
Mechanical design, but I think there are challenges on the materials as well. Is that correct? Or maybe they fit, the existing materials, do they fit?
You know, material choices come into the mechanical design to get the properties you want. That's certainly the case. And there's a lot of work, you know, that can be done on the materials side. Where I'm working inside the heart, imaging is one of the biggest issues. You never know if, you know, your mechanism isn't good enough, or it's just that you can't see well enough to use the mechanism well that you have. So that's a, you know, I would agree with this issue of sensing, imaging, but balancing that at the same time with, it's got to be as simple and cheap as possible. You know, I go to the National Institutes of Health for funding, and most of the reviewers are clinicians. And whenever I shoot down, you know, I loved a lot of the talks I've heard yesterday and today, where you're saying, look, here's this cool technological idea. And if I ever write a proposal in that way, you know, the clinicians say, too complicated, never gonna work, forget about it. So, you know, it's always trying to figure out what's that minimum, you know, you've got to have the technology in there somewhere, but what's that minimum, most simple system that will solve that or address that clinical need.
Thanks a lot. Yeah. I see another question. This is a more specific question by Hadi. Hadi, do you want to just ask yourself? This is for Nabil, Federico, Christian, Caleb, Ian, who is not here.
Yeah, sure. Yeah. So I'm picking some points through the presentations. Nabil and Federico talked about curve parameterization. We had Jan mentioning use of motion primitives, also repeated in a workshop presentation by Andrew. Also, Christian talked about model order reduction. Then we had Caleb approximating external force distribution through fitting. Are we observing a trend toward a modal or fitting approach in a reduced order modeling or model order reduction framework, instead of a strong and exact formulation in the modeling community?
Who wants to reply first?
Yeah, maybe in order, Nabil, Federico, Christian.
Yeah, I guess the argument I was trying to put forth to the community was that, you know, modeling is needed, but to the extent where you have so much uncertainty in material properties and in fabrication that it's no longer worthwhile your effort to get a very, very accurate, for example, finite element model. So at some point, you need to push it as much as you can and then realize the role of control is to get you that delta. Otherwise, we don't need control. We can just do a model-based closed form open loop, right? I think that's the point that I was trying to get. I think model reduction has a huge goal, a huge role in improving the scaling issue of modeling and controlling complex soft systems. That's part of the reason why, you know, Andrew's work has been also looking at, you know, model shape approximations, approximating the direct kinematics using, you know, product of exponentials formula. You've seen also Dr. Michiyama's presentation yesterday with his discrete approximation of the curve. All of these, I think, are ways to reduce the problem into something that we can solve without much sacrificing fidelity of the model. And I say that while emphasizing the need for methodologies to update the model for parameter changes or for interaction changes. For example, a soft robot operating in free space is a different model than a soft robot operating under constraint, right? So you need to be able to have that sensing ability and that model to update the kinematic model and static model of the robot itself. I'm not saying that you don't need fancy, you know, differential equations to solve. You certainly need them. It's just you do need to realize that there's so much you can do with these approaches for practical problems with high order of complexity, and you need to kind of balance it at some point.
Yes, I cannot agree more with Nabil about his comment. I would even push forward. I mean, for me now, model order reduction is modeling. I mean, that's exactly modeling at the end. So it is where there is the creativity, and it is exactly the way. So you have a problem, you try to fit the best reduction. It's like a cloth. So you try to dress your problem with the perfect fitting cloth. This is modeling for me. Yeah, and I hope I will continue in this direction. Yes.
Any other replies?
I wasn't asked the question, but if you don't mind, I'd like just to share a thought, which is I think it depends so much on what you're doing with the model, right? So for control, if it's not tractable, that's one of the reasons we talk about model order reduction and simplification. But I think even in design, the space is so huge that if the model is intractable, you're not going to search very much of the design space. And this is something that I personally haven't done a lot of work in, but I want to, which is, you know, we talked about applications. If you define certain force profiles or compliance characteristics, rather than thinking about it as building a robot and then getting it to do something, thinking about what is it that I want this soft robot to do? And I have all this ability to build it in a way that I've never built robots before. So can I define characteristics of a task? And then how do I search that design space with all the possible actuation and materials? And I think one answer there is the models have to be simple if you're searching a really large space to get into the right area of the space for your task. And then maybe you use more, you know, advanced and accurate models. But I think this kind of relates to one other point too, and I'll just be really brief, but I think one of the things we're missing there as well is metrics. I mean, it's really hard. So I mean this as the highest compliment. Caleb's robot, where it was twisting and had actuation, that was the coolest idea. And there's a lot of cool ideas, right, in the workshops that have been presented. And my guess is it's really quite good, but I don't know how good it is. And that's kind of the same across all of the different soft robot actuators. Is do we have ways of comparing them? So let's say I do have specific characteristics I want for a task. What actuator do I go to? What type? What actuation method? Do I go to fluid or tendon driven? Or I don't know. Me personally, I don't have a good feel for those kinds of things and those trade-offs. And I think that will be important eventually.
Hey, just to respond to that, Nabil and I submitted a proposal to develop design tools where one could compare all of these technologies. It got shot down so badly. Nobody wants to fund that.
This was the proposal I was most excited about. This is the one that was completely butchered.
I got a career proposal rejected on the same topic. But anyway, I think it's important.
So going back to performance metrics, I just wanted to give you a parallel from the rigid robot world. People have been arguing about performance metrics and you know, metrics over the Lee group for 30 plus years without a consistent agreement. A metric doesn't necessarily exist, but there are arguable measures, what we call performance measures, that you could rationalize for, right? So I think it's easy to draw parallels to soft robots with these, and there's also quite a bit of work on the energy side of things in terms of comparing, expected efficiency and energy density of an actuator per unit volume. Plenty of that published on pneumatic actuators. Substantially less on soft versions of pneumatic actuators, right? So that is completely uncovered. But now you're also seeing other types of actuators, like electroactive polymers or twisted wire actuators, and all of those variants are coming to play into the soft robotics world. The problem right now is that there isn't a unique way of modeling them. Michael Yip is taking an approach to try to reduce these into just a simple input-output model for all of these types of, or at least a subset of these types of actuators. I think it's a useful start for the community to lower the barrier for entry. But in terms of performance measures, it's difficult. It depends on what your task is. That's why I said task-based design. I mean, if you want to design your robot to go inside the body and comply inside the body, that's a different task specification than controlling something at the tip. So I think it's going to be very, very hard to argue a uniform set of performance metrics for soft robots. I'm not arguing against it. I'm just saying you're going to have to define those for sets of tasks, I think.
Yeah, I think the other thing is metrics. We always think of like a higher metric being better, but that's not even what I mean so much as like trade-offs, right? I mean, just a way to quantify where in the design space this actuator fits versus another actuator. In some sense, you can think of it like almost like literally like machine learning classification. It's like these kinds of actuators, because they have these values and these metrics, they can do these kinds of tasks, and these other ones can do these kinds of tasks. Because I agree, I mean, they're really task dependent for sure, but it'd still be nice to have tools to compare and talk about that even.
I wish you had been on our review panel.
Okay, can I proceed with another point that is raised in the chat? It's from Ida Parvash. It's about vibrations. So considering the slender structure of continuum manipulators, vibrations of the tip in dynamic motions in experimental tests would be problematic. How can we suppress these vibrations? Who wants to share some experience on that? Nobody. It means that it's really an open problem.
I mean, maybe I think that's exactly the roles of control, right? As much maybe one can say that one of the problems for this vibration is that they are not actuated, no? So you don't have an actuator to suppress directly those degrees of freedom. You can use the degrees of freedom that are controllable. And if you can observe the full state of the system, in principle you can, and if you have enough bandwidth in your actuator, you can in principle inject energy in the right way to suppress those vibrations. Yes.
There are nice works looking at layer jamming as a means to dissipate energy. I believe Kaspar Althofer was looking at that, Jessica Bergner, and possibly Ariana Menchasi, I believe, did some work in this area. I'm curious if anyone has tried input shaping for vibration suppression at higher order. Marc, have you done that?
We've done some input shaping. This was not so it's not for a soft robot in the sense like we've been talking about. It was for a Baxter robot, so 7 degrees of freedom. And essentially what we did is made them really, really compliant. And then we did feedback linearization in order to make input shaping work. And it just turned out that it did some really funny things. So any kind of disturbance, right, because input shaping is open loop, any kind of disturbance just made it not have great performance. But a really similar technique is this kind of model predictive control or something like that, where the key is just that you have a long enough time horizon and your model predicts the oscillation. And if you have those two things, then, and you have enough bandwidth, right? I mean, the hard part is you either have enough bandwidth that even in a short time horizon, you can do something about it, or you have a long enough horizon that you don't need a ton of bandwidth and you just move in a smart way. So I don't excite those oscillations. Anyway, that would be some of the things we started to look at and have tried before.
Thanks, Caleb, for sharing Walker's work on that in the chat. It's in the chat. 2 more points because our time is running fast. So one is about subcontrollers. So most of the rigid robot control strategies rely on efficient and accurate subcontrollers for the actuators in torque or in position. Do you think that more subcontrollers need to be developed for soft actuators to enhance global robot controllers? Is this a possible way to go? who has any experience on that.
I don't, but I don't like silence, I will speak. Maybe, in my opinion, probably the problem here is that there is not that much subsystem in soft robotics. This idea of subsystem is a little bit blue. I think we have discussed and said this in different contexts. One of the issues probably is that you cannot divide your system so clearly in subsystems. So you have really only one holistic system that you have to control. That's, I think, in my opinion, how I would approach the soft robotics in this sense.
If I may add something, I think that I completely agree with Federico, but I think there is also another ingredient here, which is that in rigid robots you have really to start taking into consideration the dynamics of the actuators per se when you go in very fast and very dynamic motions. So, and right now in terms of soft robotics, as we already discussed before, when you try to do very dynamic stuff, either you use machine learning or I mean, modeling of actuated soft robots that works in dynamics condition is something that it's starting to appear now, and as we saw in these two days. So I think that looking it from the model-based control perspective, simply we didn't, as a community, get yet to the point in which the actuator dynamics needs to be handled. It's kind of still a second order effect.
Thanks, Cosimo. There is another point on the metric. It's Joshua Fishman. So another kind of metric in the broader robotics world might be the DARPA challenges, where lots of different designs compete in a single broadly defined task. Is there scope for something similar in soft robotics specifically? If you allowed me, I have an answer here. I perfectly agree that competitions, challenges can be a way to measure performance in robotics. And actually, in soft robotics, we made that. It was, I mean, the first one that we organized in Italy was in 2016. So it was 1 year later, the latest DARPA challenge that was to 2015. And actually, the idea was exactly to demonstrate what soft robots could do. And we wanted to demonstrate two things, actually. That soft robots can do at least the same tasks as traditional robots like grasping, locomotion, and so on. And second, that they can do more than this. So they can do grasping, but with delicate objects, or locomotion, but in uneven terrains and things like that. So personally, I fully agree that it's a nice tool to measure performance and also to raise the bar of the technology a bit. And now there are some competitions done at every RoboSoft conference and maybe also ICRA and so on. So it is a possible way. Anybody of you did ever participate in the contest? No. It was done, to my knowledge, at least 2016 in this event. Godaba participated in ICRA in Singapore. So it was 2017, right? Yeah, I think so. Very good. I don't ask if you were among the winners. beautiful. They were among the winners, so congratulations. Okay, so I think I read all the comments that appeared in the chat and the questions. If not, please interrupt me and speak up if you have more comments or questions, because we are reaching the end of the time that we devoted to this final discussion. Which is also the end of the workshop. And I think they were 2 long days, but very, very rewarding in my opinion. Exciting talks, exciting discussions. And I think this workshop put another brick in building this solid soft robotics community, and also progressing in modeling and control of them. So I'll leave you the seconds if you have any concluding remarks to add.
Yes, I just would like to thank again everyone, the co-organizer, all the speaker, all the participants. It's been really nice to me also, as you mentioned before, it made me feel less, I'm missing this. Now I'm realizing how much I'm missing this interaction. Thank you so much, everyone.
Thank you, everybody.
Yeah, thanks again.
Thanks from all of us.
Thanks again to all the speakers. Thanks for staying so long and participating in the discussion. And again, very many thanks to the real organizers. I am one of the co-organizers, but who did the real work was Thomas, Cosimo, Federico, Hadi, and really thanks to them. And again, also for giving us the opportunity of this live events that now we miss a lot. I mean, meeting and interacting lively. Okay, so we are perfectly on time. It's 7 o'clock here in Italy, so it's 6 o'clock GMT, and we are supposed to close here. So bye to everyone. Stay safe and healthy, and best wishes to all.
Thank you, Cecilia, as well.
Thanks.
Thank you.
Bye.
Bye-bye.
Bye, everyone. Thanks, Cecilia.